Hi. We will take just. So we decrease the volume a lot. So people have to speak like that. But I think it's much better in the room and in the video. Okay. So we're going to begin. So yes, you have to speak here. Okay. Much more here in remote. Okay.
Hi. I want to start by thanking the organizers of this conference for their efforts under trying circumstances. I know we would all rather be in person, but I appreciate the time and thought that was put into reinventing this conference. I also want to thank you.
Oh. I did not. That's not. Oh, okay. Okay.
We speaking.
Okay, welcome everyone to this session. It's called Novel Approaches to Abundance Estimation. We have a great lineup of talks. And our first speaker is Charles Yakulik from U.S. Geological Survey. Please take it away.
Thanks, everyone.
I want to start by thanking the organizers of this conference for their efforts under trying.
In your. It maybe recorded me while I was making the slides. Can you mute me over there? I'm worried about what might be in there.
Sinon, il faut juste supprimer le truc en bas à droite.
You're not speaking anymore?
Okay. All right, thank you. Well, I seem to have managed to be both remote and here. Thanks for your attention. I know that must be very hard after that great lunch, and hopefully you are not getting into a nice post-lunch snooze right now. Thanks again to the organizers, and I also want to thank my co-authors here. I apologize for the length of my title. I was looking at it last night and realizing that it was absurdly long. But anyway, what I want to talk to you guys today is some ways of thinking about Jolly Zebra models that allow for integration with other data types, I think, in a perhaps a more straightforward way. Next slide. Oh, no, I have that. I was talking to me. So just start with, for folks, I mean, many folks in this room are familiar with the Jolly Zebra, but just to remind you, that what distinguishes a Jolly Zebra from a CJS model is that we are also thinking about the unmarked population that's out there. And so whereas, let's see, whereas typically we might think about how the marked, the individuals are changing through time, and even how new individuals are coming in that are either old individuals you missed the first time or individuals that came in between. We're typically conditioning on when things get captured. And the point of Jolly Zebra is that we're trying to make inferences about that unmarked population, depending on how we parameterize it. And some of the key assumptions are we're always assuming that P and phi are the same for the marked and the unmarked individuals. That's how we're able to make this inference. And if you go back to the original papers, they didn't include recruitment likelihood, but they derived it. So you got an estimate of P, you use that, expand your unmarked catch, and then you would sort of rearrange that to get at what recruitment must have been to explain the changes once you account for survival. And there have been many adaptations of the Jolly Zebra model over the years. You know, I think as often is the case, the program Mark the General Introduction has a great review of all these different types of Jolly Zebra models. They differ in which parameters are used to represent the recruitment process, and they make more sense in different situations. They differ in whether they condition on individuals seen during the survey or not. And recruitment abundance are often derived from these models, but they're never central parameters, the actual number of recruits or the actual abundance. And pop-in is one that I'm going to refer to later. That's probably one of the more popular ways of parameterizing in terms of the probabilities of entering the population at different times from a superpopulation. And so before I go into some of the talk, everything that we present here is based on marginalization. This is just a quick little plug that if you're somebody that's working in a Bayesian context, this is a way that can be quite useful for increasing the speed of your computations. I like to think of it as coding your Bayesian models like you're a maximum likelihood person. And it is sort of the thinking that goes through that more. And so we've done some work in the past. This is with the CJS, just showing how much quicker you can go by going from, even within a software, by marginalizing, or by going to software that are only supporting marginalized approaches. And so a lot of the simulations I've shown here, and this is particularly important when you start to have runtimes that are days or hours long and you're not that patient. And this is just an example recently looking at that pop-in parameterization and how you can make it quite a bit quicker through marginalization. And more generally, these are looking at a large suite of models. These are more robust design or occupancy, and these are actually CJS models out here. So getting back to the main part of the talk, the question I wanted to ask is, what about if we model capture these conditional on capture, i.e. we take part of the data and we model it using a CJS, and then we use counts of unmarked individuals in another part of the model in a joint likelihood. And some reasons to do that is I think it makes some more intuition about what's going on at the population level, and it's also going to facilitate integration. And why might this be a bad idea? You can see down here, so this is the unmarked population, and we're saying the unmarked population is related to how many were unmarked the time period before, the ones that you took away, i.e. that you marked, so this is sometimes a UIT, times survival, and then your new ones. And then we link that to data here. YT is the count of unmarked individuals through a Poisson. So when does this assumption do well? Well, we know a binomial becomes like a Poisson when you have a low probability of success or you have a high number of trials. That's, when it asymptotically, a binomial becomes like a Poisson. So those are some conditions where we might think that this approach would do best. And one thing about this approach here is it often requires constraints on these recruitment parameters to avoid negative values, not unlike what happened in the original derivation where they're deriving it. And then taking it one step forward, though, we could say, what do we lose or gain if we just model all counts of all individuals, if we don't have information in our count data on whether they're marked or unmarked? So again, here, defining N as the number of individuals available occasion T in the likelihood, and we have recruitment here. And again, we're using this Poisson where P can be time varying. And we lose precision by aggregating unmarked and marked individuals, but we don't have to worry about that constraint. And that's one of the potential advantages of taking this approach. And so to look at this, designed a simulation study in which we had 100 simulated data sets. We took an empirical Bayes approach. And for this first part, we had no random effects. So we're just assuming constant P, phi. And we had varying recruitment and abundance. And so 7 occasions, survival is 0.75, and we're going to look at 3 scenarios. First one is there's a high probability capture, just set at 0.75, and a low abundance. Second scenario is there's a high P and there's a high abundance. And then the third scenario is the one where you have a low P and a high N. I would do a lot of my work in fisheries, and this is the situation we're often in. And so what I'm going to do is I'm going to fit these using a pop conversion, as well as models where we're using either the unmarked count or the total count to get at abundance. And because we have a short amount of time, I'm just going to give you sort of the verbal summary here. The relative bias, the coverage at the 50% level, or the coverage at the 95% were indistinguishable. They're all behaving well. They're all at or above their nominal levels for the coverages. And they're indistinguishable within each scenario across the 3 models. Precision of alpha P and the initial abundance are also indistinguishable within each scenario across the models. So you're not having a big effect there. Precision on the recruitments are indistinguishable between the pop-in and when you rely on unmarked catch. When you sort of aggregate the marked and the unmarked, you have higher CVs under the high P scenarios, but when it's low P, there's really no difference. Okay, great. So we have another way to do Jolly-Sieber. Congratulations. So why bother? What I would say is that focusing on N or the unmarked and the marked population, parts of the population in a JS model allows for more intuitive linkages to a whole suite of state-space-based approaches. There's a lot of models that we have out there that are essentially state-based, where you're talking about Gompert's model, Dale-Madison approaches, where you're using an N mixture to get at the actual linkage between your data and your underlying. And occupancy, and if you're in the fisheries world, there are models that others might not be aware of, but have similar types of structures. So if you have other count data, you can introduce a second capture probability for that data type in order to do integration. So here, a second simulation study here, 100 simulated data sets. We have 20 occasions. The first 10, we only have count data. The second 10, we have both market capture and count data. These are the conditions for abundance and recruitment. And one key thing here is that I've done this both with this assumption without, and this one we have 2, we have new recruits are distinguishable from older ones. And that state does help quite a bit. And these are the distributions we assume for P and Q. They're varying by time, but they're from a distribution like this. Phi is from a distribution like that. And what we find is that there's decent precision, even when you have other counts, by integrating these two types of data. The coverage is a little bit below nominal values. It was about 42, 44% at the 50% level, and it was about 90 at the 95%, but it's doing okay. And there is a slight negative bias when only count data is available. It was about 10%, but it was actually about 5% here because we're in that place where low P's lead to some bias to begin with. And then we can go and we can actually apply this to some data. This is some data on rainbow trout populations in the tailwater of the Glen Canyon Dam. And this kind of helps us to understand some of the environmental drivers by knowing which are at least fairly good years in that pre-period and what are some not as good, even though there is less precision here. You'll see we're on a log scale. And clearly, as you might expect, doing marker capture helps and you get much better precision. And with that, I'll take any questions. Thank you.
Thank you very much. We have 2 minutes for questions.
Okay, is it on? Okay, so I was just wondering, I'm one of these people who uses marginalization to make stuff run faster, but I mostly use the marginalization other people wrote, and it's magic to me. I mostly work with Nimble and the marginalizations for latent states that were written there, and I was just wondering is it the same approach or are there different approaches to doing it? And do you know anything about how they compare if they're different?
Yeah, I've talked to Perry some about this. I don't have much experience actually working in Nimble. I started working in Stan for a bunch of other problems and I've sort of stuck there. But I have talked to Perry about the sum. Similar, but there are specific situations where doing it in Stan can be quite a bit quicker. And then there are some other scenarios where Nimble can be quite a lot more quicker. And so it's, and I don't have a great answer of like exactly what those conditions I know. I just know from having a beer with Perry and talking it through that there are situations in which one seems to perform better or the other. So it might, I guess it depends on your application and how much you really want to speed things up and how much, yeah, you're going to be doing the same thing over and over again, the degree to which you want to figure out which way is a quicker way. But you know, what's going on in the underlying math is the same either way. Yeah.
We can take another question. Okay, if there is none, I'm going to ask a question. For cases that we cannot actually count the data, like we collect presence and absences, do you think the model can be modeled at the observation process as a binomial and work with that, or it has to be counted and pass on?
No, you know, I think one could imagine how you could integrate, you know, sort of either in an occupancy framework, you know, where the data is occupancy data, but you assume a latent distribution of abundances, that there are certainly ways that you could start to integrate those data, you know, depending on the specifics. There are assumptions that go into that. And so the extent to which it's, you know, a good representation will depend on the specifics. But yeah, there's no reason why. I mean, any model, I think, where you have a latent time series of abundances, which is quite a few, there's a means to integrate there. So. And, you know, one thing I didn't emphasize in here too is that in the specific application, the count data comes from a slightly different scale than the mark recapture data. And so we were able to get at you can either make that Q unbounded so that it can be higher or lower, or you can actually try to come up with some estimate of the difference in scale between the two sets so that you can integrate and make more sense of what you're getting out of it. So, yeah. Scale is always an issue when you integrate data. So.
Thank you very much. Our next speaker is Diego Rondon. He's from Oulu University in Finland, and his talk is titled "A Bayesian Multi-State Model for Estimating the Effect of Inbreeding and Age on Population Dynamics." Please take it away.
It's not my slide. Okay, yeah, that looks like mine. Thank you very much for having me here. My name is Diego Rondon. I come from Oulu University in Finland. I'm going to present to you this Bayesian multi-state modeling for estimating the effect of breeding and age and population dynamics. This works made in collaboration with Samu Mantuniemi, my co-assessor from LUKE, which is the Environmental Resource Agency of Finland, and some other professors from Oulu University, Johnny Aspi, Laura Kubis, and Mikko Silampa, my main supervisor. Oh. Sorry. Goes crazy. Okay, so we have a problem with small population is that when a population size starts to become small by any chance, there is a high chances of inbreeding. What we mean with this is mating with relatives is more common, which has been proved that comes with a loss in genetic variability of information on the DNA of the individuals, and it affects the fitness of the individuals as a whole. So we are like in a constant loop between I'm small because I'm mating with my relatives, and then low genetic variability, and then fitness, and so on and so on. This is called extinction vortex, and is usually stages that occurs for an individual, for the population before they go into extinction. Since it has been proved that an increase in inbreeding, it has a decrease in the population sizes, and survival probability, and number of offsprings that they produce, and just the overall fitness as a whole of a population. So what I want to do is I want to develop a model that allows the joint estimation of both population sizes and the effect of age and inbreeding on a population, in this case an open population that is going through this inbreeding effect. On the way I will find, I will answer questions such as how hard is to capture this effect, and how stable is the model at different population sizes, and what about the population trends. So the first step to develop this is to create a simulated population. My population consists of three main steps. First one is the survival probability, where the individuals, where an increase on inbreeding F or an H will decrease the survival probability or the time of life of my individuals. Secondly is the number of offsprings that they produce. So as inbreeding and age increases, again, less offsprings will be introduced to the system. Finally, the way I keep track of my information is via a ancestry matrix, or a genealogy information. In this way, I can keep track who relates with who and how much does it affect. The model, the simulation is an open population model, so we allow for immigrants to come at chance. And these immigrants have no relation to the actual population size. So once my population is simulated, I can easily sample several times and develop my data sets and build nice models. In this case, the model that we are proposing, it's a multi-state modeling, just as we know it in statistics, a hidden Markov model, in which we have like a hidden layer, which is the state of the individuals that are in, that separates from males and females and youngs and adult individuals. These transitions between the states are governed by the transition matrix, which I will go more into details. And the observation layer, or the emission probabilities, which is like if I don't see my individual, if I see it as a young or if I see it as an adult, which are governed by my emission matrix theta. And the process is just simply a development process, which uses categorical distribution to model the next state of my individual is in relation to my previous state, and my transition matrix and my observation matrix as the state of my individual and my emission matrix. So if I go a little bit more into deep into how this survival probability is, this transition matrix is going to work. The survival probability is going to be modeled just using a basic GLM model that uses my parameters, age and inbreeding. as a whole. And I will try to find good estimates for this. Let's see. Also, we introduce a smooth term in the first term. So the number of individuals, the number of individuals that enter the population at time t is going to depend on the previous time point, plus some random variations. And finally, the number of individuals at each generation t is going to be just the basic count of the individuals that are alive in the system. Okay, since we are trying to model a wild population as much as we can, we have to account for the individuals that are not observed. So we use data augmentation, where I create just an extra data set to accomplish for those not marked individuals, but I also have to augment my covariates inbreeding and age based on of individuals that I did sample. Okay, so here we build a model in Nimble. We use 70,000 chains born in period for each. We did 50 replicates of each data set, and each replicate hosts 3 chains with different starting values. You can imagine that it takes a lot of time to fit all those chains. So we use Pukti, which is the supercomputer of the Finnish Center for Scientific Computer, to facilitate things. These are the results from the simulated population. The starting values are pretty much the same for the 2 scenarios that I proposed. Just the main difference is that the parameters for the survival probability. The first scenario, it's called a decline population, and we let all this white part just to get some variability into the simulation and focus on this gray area. We can see here the decline, the population is going into a decline. And the bottleneck scenario, we call it bottleneck because in order to get this wiggly part, we manually introduce some individuals before the population goes extinct in order to reassemble. We are trying to keep the population alive. Under these 2 gray areas, we are going to focus on sampling having different sample size of individuals, mainly 40, 60, and 80% to see how stable the model is. We want to see the estimate of the population size. So I have here in this case, the decline scenario with the sample size of 40%. The blue line is the true simulated value, while the gray dots are the posterior mean of each chain. We can see here that when I have small sample sizes, there are some chains that tend to deviate from the true posterior, so they converge to a non-ideal posterior distribution. While if I increase my sample size, I will get more nice and smooth results of population sizes. If I collect this across all these 150 chains, the effect of my parameter inbreeding in the different scenarios, I can see how the distribution of this is. In this case, I have the decline scenario with the 3 different sample sizes, 40, 60, and 80. And the dotted line is the simulated value. So I can see here that there seems to be an identifiability issue, because the higher the sample size, the farther it gets from the posterior distribution from the true value. While if I talk about the bottleneck population, I can see that having a large sample sizes helps to having a correct estimation of the posterior distribution, while if my sample size tend to be small, the parameter is not going to be correctly updated. But if I move to the parameter age, I'm going to be able to see that if I have relatively medium sample size and high sample size, the parameter behaves the posterior distribution behaves very similar to the true value, and also in the age. So yeah, finally, as a conclusions, we were able to see that we can have an accurate estimation of population sizes and trends, of course, from the population, even if we have low population size, a low sample probability. The survival coefficients can be easily obtained if I have high sample sizes. And yeah, small sample sizes may not be very ideal in this case. And that augmentations were particularly good, especially in this case where we're trying to simulate wild individuals. Just some references, and yeah, thank you very much.
We have 4 minutes for question. While the audience is preparing questions, I have one to ask. Could you elaborate on incorporation of age when the data is augmented for individuals you have never detected?
Yes. Maybe if I go to the slide, it's going to be more easily to understand it. So I found out with the help of my professors and several iterations of trying to make the model work that if I augment the data, the covariate parts from the, like if I take a sample from the population that I saw and I make it look like, okay, these individuals that I did not saw have a similar age distribution or a similar inbreeding distribution to the ones that I did not saw. It's going to help to the model to converge to more ideal values. This, of course, brings the assumption that the individuals that I see and the individuals that I do not see have similar distribution. But yeah.
Thank you.
Okay.
There's no more questions, so thank you very much.
Thank you very much for your time.
Our next speaker is Rémi Fay. I hope you pronounce your name better than me. Okay, his talk is titled Modeling Misidentification and Capture-Recapture Experiments. Please take it away.
Well, hello everyone. So indeed, Rémi Fay, working on capture-recapture in presence of misidentifications, and we're focusing especially on low recapture cases because it's part of a project that aims to apply capture-recapture to mosquito larvae. So we are expecting both misidentifications and low recapture cases. So I'll be talking about misidentifications, the kind we are expecting. The latent multinomial model that can deal with misidentifications will see its performances in low recapture cases, and we'll see also what kind of information we can add into the model to improve its performances. So first, how do we do capture-recapture with mosquito larvae? Well, we take a larva, put it into DNA-free water, and after 24 hours, release it and extract the DNA. So we got eDNA, and if we do it several times, we can have capture histories. The problem is that the DNA will be of very low quality and quantity. So, for example, say on day 3, we will fail to recognize the individual. So we do observe the genotype and we say, oh, never seen this genotype. Out of luck, we create a new individual that does not exist and that we will never see again because it does not exist. So you can see it adds a lot of zeros in the table, and this will lead to overestimating the population size or underestimating the survival. So what can we do? Well, in the classical case, if there's no misidentification, then we would have these histories, for example, and then why the observed histories frequencies would follow a multinomial. That's the classical case. But say the last history here is a misidentification, then why does not follow a multinomial anymore? So what we can do is working on latent histories. The idea is to put back the ghosts, the misidentifications, into histories that could have generated them. And then we mark them with a 2. And then we have X, the latent history frequencies that follows a multinomial back. And now we can construct an MCMC to estimate the population size or the survival. So it does work, but how does it work with very low capture rate or low capture rate? Well, to find out, we simulated capture-recapture with capture rate between 0.1 and 0.4. We simulated identification rates between 0.8, so very low, to 95%. We applied it on 5, 7, and 9 capture occasions. And without any prior information, what we get is that here, the gray line is the true population size. With capture rate at 0.2 or more, it seems to work pretty well. And in any case, well, obviously, it's not very good with 5 occasions, but just improving the number of occasions is enough. But when we drop the capture rate to 10%, we can see that even with 9 occasions, it actually never works. And what's worse is that the NCMC actually does not even converge with 5 and 7 occasions. So first idea to improve the performances was adding prior information on the identification rate. So for this, we can test the identification protocol on non-individuals, and then we can very easily integrate this information into the model. The prior is very easy to integrate. And now the first result is that it always converges for 0.1, so that's already pretty good. And what's more, the true population size is always or almost always into the 95% interval marked by the triangles. So that's already quite a good thing, but still it does look a bit underestimated systematically here. So can we do better? Maybe. What did we do? We took DNA, we observed genotypes, we combined them into capture histories, and then we only gave capture histories to the model. So obviously all histories with a single capture are equally potential ghosts, so misidentifications. And we know that's not true because between different genotypes we observe, there will be different missing loci, there will be different, the genotype quality policy will be different from one to another. So the overall quality of the observation will be different. And if we can give that to the model, then we will get closer to the truth that lower quality samples have a higher probability of generating a ghost, so misidentification. So to do that, we switched from a constant model where alpha, the identification probability, was constant, and so all capture had the same probability of being properly identified, to a probit model, where now the identification probability depends on, is a function of the covariate or the quality of the observation. We implemented it and we simulated capture-recapture based on this new model. And so on the left, it's the old model run on the new simulation, so the results are the same, quite happy with it. And the new model, the first thing is that actually it does converge. The NCMC converge except for probability, for an identification probability of 0.8 and 5 occasions, but you should never get into that situation, so it's already okay. And now the estimation are not systematically biased anymore. So that's also good, good result. The next direct step would be integrate the prior information into the new model and see how it happens, see what happens, but it's a bit trickier than with the other model. So we did not do it yet, sadly. Just another thing is that you can see that the identification rate from 0.8 to 0.9, the triangles are the average 95% interval, and we can see it reduces a lot when the identification rate improves. So this shows that even if we have a model that can deal with misidentifications, we should experimentally reduce as much as we can the error. So, small conclusion, we can do capture-recapture with misidentifications, meaning that we can use eDNA of low quality, low quantity, and we can allow for misidentifications and still estimate properly the population size or the survival. But we should still pay attention to the misidentification, and 20% misidentification might be a bit too much. Low recapture rates, they are a problem, but they can be accounted for either with a prior by testing the identification protocol on non-individuals, or by adding information about the quality of the samples. We implemented the model with Nimble on R, and there are already some codes available on GitHub, but we plan to release the package someday. Lastly, there's a preprint awaiting for review in PCI. So if you're interested in, just check it. And finally, a few words about the potential of the model. I've shown results for closed population, but we also implemented open population. We implemented transition and migration for open and closed population. The model can adjust itself to different kind of misidentification. So the framework is quite malleable. And I'd say the next big step for the model after adding the quality of the observation would be to add as an information how close the genotypes we observed are from each other in order to know which history could have generated what error. And that's it. Any question?
We have 3 minutes for questions.
Great results, and I have 2 questions that are connected. So the first one is, when you read your misidentification, is only a loss of, so you cannot read one of the genotypes as another one that is existing.
Yeah, we suppose that when the misidentification only create ghosts, and that the panel to identify the individuals does not allow for confounding 2 individuals. But that's that's what this paper does. Is the only misidentification they consider is thinking an individual A is actually B, and so it can be done.
And do you estimate misidentification probability as a separate parameter, or is it?
Yeah, we only consider one kind of misidentification at the time, and the misidentification rate is one parameter of the model. So we only give the histories, and the model estimate how much misidentification are made.
Okay, I have a question. What are the costs of these models? Like, have you looked into an approximation of the time of the computation? Should we be using these models always? Like, especially the application of a model like this on a larger scale monitoring data set, let's say, of mammals that is hundreds of square kilometers. Would this be a useful model for such a problem?
Well, I guess the real interest of the model is monitoring population where you can only do capture-recapture, and in cases where if you throw out very low quality data, say medium, if you throw out this data because you only want very good identifications, then you might not get enough data to estimate properly. So the interest in the model lies in using medium quality data, and for that there is a real interest. And about like computing time for these simulations in closed population, single state with 9 occasions and only time heterogeneity for capture, it takes 5 minutes after after having compiled the model. So it's very, very good. If we extend it to multi-state, then it gets much slower, but 2 hours is still.
Okay.
When the sampling occurs in the field, are they going to the same water bodies day after day, or are they taking multiple water samples within?
Yeah. Well, the plan is to go, say, on 10 days into the same pound and taking the individuals, releasing them into the pound, and coming to the same days after days.
So I guess in that, have you thought through what could happen if you had violations of closure and how that might show up as misidentification? Because I mean, I assume if you have some individuals that when you go to use this to monitor come in only at the end of the period of closure, or come in or are leaving right at the beginning, that could show up as an abundance of sort of single genotypes that you might assume are misidentification when in fact it's violation of closure.
Yeah, well, we implemented it anyway in open populations, so with Jolly-Saber, Cormac Jolly-Saber framework. So there's no closure any way to think about, and yeah.
Thank you very much. Our next speaker is participating remotely, Rishika Chopara, and her talk is titled "A Framework for Goodness of Fit Testing in Ecological Modeling."
Hi, my name is Rishika, and today I'll be presenting a talk titled "A Framework for Goodness of Fit Testing in Ecological Modeling." So I'll be presenting research I'm doing as part of my PhD with Dr. Ben Stevenson and Professor Rachel Feaster. Goodness of fit testing is a really important step in statistical analysis, as it allows us to determine whether our results are likely to be reliable and valid. However, when working with models like ecological models, goodness of fit statistics such as the deviance often don't come from the distribution we assume they come from. So we'll look at how we can get around this problem when using the deviance to assess model fit. So traditionally, the deviance is defined as twice the difference between the maximized log likelihood for the saturated model and the maximized log likelihood for the simpler model that we're considering, and we'll refer to this quantity as the model's empirical deviance, and we'll label it D subscript E. Now, alternatively, we could evaluate the log likelihood for the simpler model at the true parameter values, and we'll refer to the resulting quantity as the model's generative deviance, and we'll label it D subscript G. So from now on, unless we explicitly say otherwise, when we talk about a model's deviance, we'll be talking about its empirical deviance. The result that's commonly used is that under the null hypothesis that a model fits the data well, its deviance comes from a chi-square distribution where the degrees of freedom is just the difference in the number of parameters for the saturated and the simpler model that we're considering. Now, this assumption has to hold for us to be able to take the model deviance and compare it to its corresponding chi-square distribution to calculate a p-value that we can then use to assess model fit. However, this assumption doesn't hold, and any p-values we calculate are unusable when we're working with data that doesn't contain enough information. Specifically, when it comes to count data, this assumption is invalidated when working with sparse sets of counts. So these are counts that have low expected values like the ones you can see here. For example, if you work with capture-recapture or spatial capture-recapture models, you'll find that it's quite common to find yourself dealing with sparse sets of counts. In fact, it's quite common to be dealing with counts that have expected values close to 0 like the ones you see here. And so when working with these models, the chi-squared assumption is often invalidated. But many people use these models, and because of this issue, they can't really use the deviance to assess goodness of fit. And so this is the problem that we look to get around. One way that people have gotten around this problem in the past is by using a parametric bootstrap, which gives us an intuitive way of approximating the distribution of the deviance without assuming that it's chi-squared. However, this approach can require a lot of time and a lot of resources, especially when dealing with sophisticated models like capture-recapture models, for example. So it's probably only appropriate to use when working with simpler models like GLMs. And so we chose to try and seek out alternative solutions to this problem. And we began by taking a closer look at the chi-squared approximation when dealing with sparse data. So we began by looking at a set of sample deviance values for a capture-recapture model that tends to produce sparse data. And we tried to overlay the chi-squared approximation. Now you can't really see it here, and that's because the degrees of freedom, or the mean, lies at a value of 4,093. Examples like this just helped us to confirm that the chi-squared approximation isn't really appropriate when working with sparse data. They also got us thinking whether adjusting the mean of the chi-squared approximation could solve the problem here. And so we started by trying to find the expectation of the deviance for a model, as this seems like an appropriate term to use to adjust the chi-squared approximation. So we began by looking at this quantity here, which is just the difference between a model's generative and empirical deviance. Now this difference is just a likelihood ratio test statistic, and so by Wilks' theorem, it comes from a chi-square distribution where the degrees of freedom is just the number of parameters in the model being considered. And because of the nature of this assumption, it holds whether or not you're dealing with sparse data, which is quite nice. So by the nature of the chi-square distribution, you can say the expectation of this difference is p. And so you can say that for a model, the expectation of the empirical deviance is equal to the expectation of the generative deviance minus the number of model parameters. To make this all a bit more concrete, let's say you're fitting a closed population capture-recapture model using a Poisson likelihood. In that case, we found that the expectation of the generative deviance is equal to this quantity here. So for such a model, the expectation of the empirical deviance is equal to this quantity minus the number of model parameters. So we are going to go back to our example from earlier, and the red line represents a chi-square distribution where the mean is set to be equal to the expectation of the empirical deviance for the model here. And if we zoom in, we can see that the mean of this curve looks really good, but its variance isn't really good enough. Now, to adjust the variance of this approximation, we'd have to work with a whole new distribution. And we realized that the chi-square distribution is just a special case of the gamma distribution. So we began to wonder whether a gamma approximation could work here and solve our problems. So we started by trying to find an appropriate variance term to use for such a gamma approximation. And we begin with the fact that if the covariance between the empirical deviance and the difference between the generative and the empirical deviance is 0 for a model, we can say that the variance of the empirical deviance is equal to this covariance here. We can also take our chi-squared assumption from earlier to say that the variance of this difference is equal to twice the number of model parameters, and we can combine these pieces of information with the formula for the variance of this difference to say that if this covariance is 0, then the variance of the empirical deviance for a model is just the variance of the generative deviance minus twice the number of model parameters. Now, when it comes to this requirement here, we've been able to use Wilks' theorem to show that it holds exactly when dealing with a normal response. And for other models, such as capture-recapture models, we've been able to use simulation and empirical results to show that this requirement holds approximately. And so in general, this expression for the variance of the empirical deviance seems to be pretty accurate. So now we'll look at the performance of our gamma approximation in the same scenario we've been looking at so far. So now in blue, we have our gamma approximation, where this curve is fitted by selecting a shape and a rate parameter such that the mean and the variance of this curve is just the expectation and the variance of the empirical deviance for the model here, found using the expressions that we've just seen. And if we zoom in, we can see that our gamma approximation seems to work really well in this scenario, which is quite a promising result. So we'll look at two more. So now on the left, we have a set of sample deviance values for a non-sparse data scenario from capture-recapture. And on the right, we have a set of sample deviance values for a sparse data scenario from capture-recapture. And now in green, we have our traditional chi-squared approximation. Unsurprisingly, it doesn't work very well when we have sparse data. And in blue, we have our gamma approximation. Once again, it performs really well in the presence of sparse data. And if you look at the tails here, it even slightly outperforms the chi-squared approximation in the presence of non-sparse data here. So overall, our gamma approximation seems to provide an improvement upon the chi-squared approximation. We then looked at the performance of our gamma approximation in a range of capture-recapture scenarios, each of which involved data with varying levels of sparsity. And as you can see here, it seems to perform pretty well. So our last step was to turn to simulation to see how well p-values calculated using the gamma approximation work at assessing goodness of fit, where the null hypothesis is that our model fits the data well. And we began by looking at a non-sparse data scenario from capture-recapture, and we produced the plots that you can see here. So in the plot on the left, the red curve represents true p-values found using simulation, and the dashed blue line represents p-values found using the gamma approximation, and we just logged both sets of p-values to create the plot on the right. So you can see in both cases the curves pretty much align perfectly. Our gamma approximation can be used reliably at the 1% or at the 5% significance level here. More interestingly, we looked at a sparse data scenario from capture-recapture and produced the same plots as before. If we focus on the plot on the right, you can see that once you dip below a p-value of 0.05, you start to see slight differences between the true p-values and the gamma p-values. But it's only once you dip below a p-value of 0.01 that these differences become of any practical importance. And in fact, the data that we used here was perhaps the sparsest data you could expect to come across in a capture-recapture setting. And in this case, we found that our gamma approximation could be used pretty reliably at the 1% or at the 5% significance level, which seems to be quite a promising result. So overall, we've developed a framework that can be used to accurately approximate the distribution of the deviance in broad generality. It works whether or not we have sparse data, and in fact, it doesn't just apply to Poisson or capture-recapture or even ecological models. It seems to be a general result. So it's potentially quite a powerful result that could be used to assist with goodness of fit testing in a range of fields. When it comes to future work, we'd like to formally determine the range of models that our gamma approximation applies to, and we'd also like to use statistical theory to justify the use of the gamma distribution above all others here. Thank you very much.
Thank you very much. Hello, Rishika, do you hear us?
Yeah, I can hear you.
Okay, thank you for a great talk. We're taking questions now. We have 2 minutes for questions.
Wow, thanks for an amazing talk. That's a great result. I'm curious, when you applied this to sparse capture-recapture data, sort of how sparse that was. I guess I'm thinking about a case where you have a long capture history, maybe a multi-state sort of model, and the expectations for individual histories get really low. Yeah, so how sparse is sparse?
Okay, so first, I feel like I need to preface my answer by saying it's almost 1 a.m. here, so my brain isn't very fast. But from memory, we were working with an M0 model. We were working with 3 sampling occasions, and we were working with a capture probability of 0.1. And I think our true, or like the rate at which, our lambda value, or the rate at which animals occurred in the region, was only like 100 or something. So it was fairly sparse data, like our expected counts were pretty low. I hope that answers the question. Let me know if I can provide more detail.
Thank you very much. There is no further questions.
Yeah. Thanks.
All right, Michelle Kisling from University of Montana, Missoula. We'll be talking about aligning statistical and biological populations for abundance estimation.
Thank you. I'm really excited to be here today. And before I begin, I'd like to thank my co-authors for their contributions to this project. Gotcha. Today I want to talk about improving inference. We draw statistical inference about statistical populations by sampling them. But what we really want to do is draw scientific inference. I said that wrong. We draw statistical inference about statistical populations by sampling them. But what we really want to do is draw scientific inference about biological populations, because those are the populations that have ecological meaning to them. We simply use statistical populations as a way to learn something about biological populations, and we hope that their inferences are in agreement. So ideally, a statistical population is the same as or accurately represents its corresponding biological population. However, in practice, they rarely align in space and time, which can lead to variable exposure to sampling and biased inference about the population of interest, the biological population. Analytically, we often view a mismatch as a temporary immigration process, though ultimately it's a detection issue. If it occurs randomly, it will inflate unexplained variance and reduce precision of estimates. If it occurs non-randomly, it can bias estimates. And although there are abundance models that account for temporary immigration, they rely on spatial and temporal replicates, or that include short periods of closure, or the ability to identify individuals during sampling. And these aren't feasible for all species and habitats. So we were motivated to resolve a population mismatch for the Kittlitz's murrelet, a small seabird of conservation concern that's patchily distributed across coastal Alaska and eastern Russia. And this species has an unusual life history that complicates abundance estimation. It's a solitary and inland nester, so unlike most seabirds, it can't be counted at colonies. And second, it's not territorial on land or at sea, and non-breeding is common. So individuals can be highly mobile even during the breeding season. And finally, the species is associated with tidewater glaciers and dynamic marine habitats, such as those that are dominated by ice, like can be seen in the lower photos here. So the only feasible way to estimate abundance of Kittlitz's murrelets is by at-sea surveys. However, these surveys are vulnerable to population mismatches that can't be handled with replicate or repeat sampling. The birds are too mobile and the habitat is too dynamic for replicate sampling, and the birds are too small and cryptically plumaged for identification of individuals during boat surveys. So we led a long-term study on the population dynamics of Kittlitz's murrelets in Icy Bay, Alaska, in the Northeast Pacific Ocean. And as part of this study, we conducted 2 boat surveys each year during the first 2 weeks of July using line transect distance sampling methods. However, in the first couple years of this study, we quickly realized that we were only able to sample a small portion of the area that the murrelets appeared to be using. And the problems were unsolvable because they were safety related. We couldn't access some areas because of thick pack ice or shallow water or very rough seas that weren't conducive to our small boat. And then we had this added problem of shifting ice flows that often changed with the 6-hour tide swings. We also were somewhat concerned about missing birds on nests, which we couldn't really deal with because this was a solitary nesting species. So in this figure, you can see our boat transects are in black, and they form the boundaries of our statistical population, which is in green. And the area in red is the area that the murrelets were using, and that forms the extent of our biological population. So to put the potential mismatch in in context, we were only sampling about 21% of the area that the murrelets were actually using. Whoops, I forgot a very important part. So to address this potential mismatch problem, we started radio tagging about 30 birds a year. And we did that for about 6 years, between 2007 and 2012. And we were tracking them at the same time that we were conducting boat surveys. We then developed an integrated model that combined boat survey and telemetry data to estimate the abundance of the biological population, sometimes referred to as the superpopulation, of Kittlitz's murrelets. And by using this approach, we were able to account for all of the components of the detection process. We estimated the probability of presence in our sampling area, which is basically the temporary emigration component, using the radio tag murrelets. And we estimated the probability of detection using the distance sampling data. I'll also note here that we also did estimate the other components of detection, the detection process, availability, and the proportion in the sampling area, but they were so close to one that I'm glossing over them. We then used the joint likelihood to combine information across both of the boat surveys in a given year and estimate a single value for annual abundance. And the likelihood included count data, the probability of presence, the probability of detection, and a component that dealt with species identification, which I don't have time to get into today, but basically addressed murrelets that weren't identified to species. And we ran this model for each year with and without the probability of presence to see how much variation in abundance could be explained by temporary immigration. So diving into results, this figure shows where birds were located during our surveys. And most of the birds outside of the sample area were found in rough seas or shallow waters. Only 4% of the birds were at nests and 1% of the birds were in ice, dense pack ice. And this was opposite of what we had hypothesized originally. Across all years, the mean probability of presence was only 0.5. So to put this in the context, we sampled only about 21% of the area used by murrelets, and they had a 50% chance of being in the sample area during surveys. Annually, the mean probability of presence on the left here ranged from 0.35 to 0.72. And the mean probability of detection on the right ranged from 0.49 to 0.77. So we found that the probability of presence varied more than the probability of detection. And here we present the posterior distributions of the annual abundance for the statistical population in blue and the biological population in red. And each plot here is a year with abundance on the x-axis. And the triangles with the corresponding colors are the CVs of the mean estimates. So, and to simplify things, I included the difference in CVs in the upper right corner of each plot. So a couple takeaways here. The posteriors for the statistical population look more precise than those for the biological population, but in 5 of 6 years, we reduced the CVs by 13 to 35%. However, in 2009, the plot in the upper right corner, we were only able to conduct 1 boat survey because of logistical issues. And the CV increased dramatically, likely because the CV for the statistical population was underestimated. But this result also suggests that the probability of presence is tightly linked to survey effort. So in conclusion, Our results showed that the probability of presence varied more than the probability of detection across years. And when accounted for, we improved precision of the estimates by 13 to 35%. But we also found that the probability of presence and survey effort were conflated, which emphasizes the importance of a second survey if the probability of presence varies. Our integrated model is simple, flexible, scalable for resolving a mismatch when repeat and replicate sampling is not feasible, such as with highly mobile species and in dynamic habitats. However, it's not a silver bullet, as it still requires some marked animals. But still, if precision of abundance estimates is needed or desired, as is the case with many endangered species like the Kittlitz's murrelet, our model offers a potential and practical solution. And most importantly, it improves inference of the population that we want to know something about, the biological population. So I'd like to acknowledge the many people that have worked on, funded, and supported this project over the years, and those that offered analytical advice. And also, given the short presentation time, I didn't get to talk about our trend results. So I included my contact information here if you'd like to talk about that more. Thanks.
Thank you very much.
Time for a break.
Great talk. It's like makes one wonder a bit, when do you just give up on counting a species? But it just made me wonder. So you have a tiny seabird that is hard to see and difficult to count. How did you catch them to put the radio tags on them?
First, thank you. I will buy you a drink of your choice for the easy question. Yeah, it's quite a rodeo. We catch them at night on the water, and which is quite challenging at high latitudes. We only have a 2 or 3 hour window, and we're in a small Zodiac with a salmon dip net and a spotlight. And basically we zoom around, and theoretically they freeze in the spotlight like a deer in headlights, and we scoop them up. But in reality, we catch like 1 out of 10 that we try to catch. So yeah, the first year we caught 15, and it took a long time, and we got a lot better at it. And then we ended up catching hundreds annually. So yeah, thanks. That was a fun one.
There is also a question from Charles Francis. How do you ensure that the sample of radio tagged individuals is representative of the biological population, as presumably you can only capture them in certain areas?
Yeah, good question. So I just mentioned that in Alaska, around the solstice, we can't capture them during the breeding period. So we're actually capturing them when they're out in the Gulf, so they're not up in the ice, basically. We have to catch them in early May and attach the radios. And then we developed a list of criteria that if the birds go off the air or they're detected elsewhere, that they're no longer part of our biological population. Yeah.
Okay, thank you very much, Michelle. Thank you. This is the end of this session. So I would like to thank all the speakers and
we are 30 minutes. Very short break.
Tu veux à chaque fois, tu peux envoyer.
Je t'avais pas expliqué.
Ah, ok.
C'est possible. Je peux y aller.
I'm showing this. Okay. And then I'm 8, yeah, and then I'm checking the line for the question. So just here, and then I'll decide. So don't worry about the time. It's because we are like a big team, so each one has a time. Yes, so we can and so, you have a new one. Et l'autre, je suis peut-être en panique. Parce que du coup, le cours il m'a dit ils vont on va plus leur donner. Les questions du coup ils peuvent les voir si... Ok, parce que là du coup j'ai ouvert, il y a la question d'avant et là, du coup c'est là où je t'ai dit qu'il y avait la personne elle veut être payée. Mais c'est qui? Il faut qu'il soit panéliste pour... Okay.
Okay. Start at 15 seconds.
So welcome back to this afternoon's second session, a series of excellent talks titled Causal Inference for Management. Our first speaker is Ramiro Munyeme. His talk from responses of macroinvertebrate metrics to the definition of reference thresholds.
Hello everyone, I am Romuald Huyem, PhD student at the Women Recovery Team Fresh School of INRAE. My presentation will be entitled From Responses of Macroinvertebrate Metric to the Definition of Reference Threshold. The plan I am proposing is as follows. From the context and justification, followed by the issue, I will briefly talk to you about the objective of my presentation, then the material and methods of the application set of the developed approach. I will dwell more on the analytical approach developed, and then I will show you the first result and conclude. As for the context, the analytical approach we present here concerns above all on monitoring ecosystems such as those in Africa, for which it is not possible to have a chronicle data, quality standard, or allocated resources. It should be remembered that for this system, it is not easy to find experts who could guide us. For example, on the duration of variation of the effect of pressure proxy on the different guides. When we know that the population growth in this region will be the highest in the coming decade, and that many warming of the loss of aquatic diversity are registered, many questions such as those on this slide are asking. More concretely, how to define reference threshold, quality standard in order to consider, at least in the short of or medium term, the evaluation of the ecological status, the basis of a monitoring program, or at best to receive information essential to their knowledge and restoration. To answer a small part of this question, we propose as a main objective to develop an approach that will use that data from a few sampling campaigns on benthic macrofauna to define the reference status of an anthropized lagoon from the responses of relevant metric to process. More specifically, in this presentation, the approach that I will present to you will include 3 steps: identifying the relevant stable metric that best respond to the stressor, predicting the responses of the metric to multiple stressors simultaneously, deducing the reference threshold value. First of all, let me introduce you to the aquatic ecosystem at the origin of this approach. It is the Nokwe Lagoon, located in the Gulf of Guinea, in the Republic of Benin, in West Africa, subject to a strong environmental constraint linked to the various activity on the lake and its watershed. Recently, it has been reported that the loss of 42% of its specific richness in fish. The few data that have been collected in recent years consists of 3 years of macroinvertebrate sampling that has allowed us to determine 76 taxa, 33 of which have been observed throughout the year are differences during high and low water period and more or less known to the literature. We also have 4 groups of data which are the physico-chemical stressor, the hydromorphological alteration, non-natural land cover, the other forcing factor. As you can imagine, the functional characterization of the Altasa has not been easy. Now, so that you have some idea of the data we have at our disposal, here is a summary of the step of the approach taken. The methodological approach consisted of 4 steps. We use a Bayesian framework carried by a GSDM named HMSC as hierarchical modeling species community. Regarding the selection of relevant metric, in first step, a redundancy analysis with linearity forcing between macroinvertebrate metric was performed. In a second step, the selected metric were injected in a Bayesian framework. The HMSC model was considered here as a pressure impact model aiming to simultaneously select the most robust and relevant metric responsive to anthropogenic alteration at the sampling site. A metric was selected when the model that explains it has at least one pressure parameter that was significantly expressive with or without natural. The Pearson correlation coefficient between expected and observed value was greater than or equal to 0.3 at the end of 3 successive HMSC analyses conducted on 2 trained subdata sets corresponding to high and low flow period HMSC1 and HMSC2, respectively, and on a selection, synthesis, analysis, subdata set performed on third party of the stratified observation randomly taken on the whole observation data, that is HMSC3. The HMSC3 analysis is initiated to allow more flexibility in the sampling period of the selected stable metric. For these three inferential analyses, the sampling of the posterior distribution was performed using MCMC chain. A normal distribution was specified simultaneously for all models. About calculation of response probability, the a posteriori probability of metric responding positively or negatively to the different level of a pressure was then collected from two equivalent HMSC models, that is HMSC Bru and HMSC DIS, of each of the pressure parameter, that is the step 3. We assume that the a posteriori probability that a metric responds positively to a pressure is equal to the sum of the a posteriori probability that the same metric, knowing different level of the same pressure, also respond positively. Now about the reference threshold. The following step 4 consisted in simulating macroinvertebrate metric responses to multiple stressor by learning Bayesian network and then extracting reference threshold value from probability density plots. The value of the intersection points between the negative and positive density curve for a low pressure level was considered as the reference threshold. The a posteriori probability of the calculated responses was compared with the responses of the metric expected in the literature to confirm or not their validity. The unknown relationship were retained as proposed by unsupervised learning. Now, so here you can see the result of the metric selection. 7 selected out of 54 tested. The implementation of step 3 gave response probability whole strength for high degradation level are presented in table 2. On this slide, you can see the directed acyclic graph that was used to predict the different responses. On this slide, the table presents the summary of all predicted reference value extracted from the density plot representing the various predicted responses of the parameter at different pressure level. It also highlights the most severe threshold value of the stressor that could be used for the reference station. In conclusion, all the selected metric gave coherent answer with each of the pressure level defining in the literature. The reference and inferential stress threshold are comparable to those existing, but with some specificity that could be attributed to the environment. The developing approach allowed to bypass the possible contradiction that often arise between the meaning given by the expert and the effect expected and induced by the pressure process, particularly in a context like ours. The approach advocates the search for a better sensitivity to the selected metric to human perturbation as well as their robustness. The flexibility and the possibility of extension of this approach to many other biological systems should be emphasized as it offers the possibility of incorporating also expert opinion in an explicit and reproducible way. Thank you for your attention.
Time for one question.
Okay, well, I have a quick question. I noticed that you grouped covariates into a number of different kind of categories. Have you considered like latent covariates or a structural equation modeling approach? An excellent talk, by the way. Well, perhaps we'll move on to the next speaker, and we can follow up later in the chat. Our next speaker is Daniel Fink, who will be giving a presentation entitled Estimating Spatially Explicit Population Trajectories with Citizen Science Data and Double Machine Learning.
Hi, my name is Daniel Fink. I'll be talking about estimating population trends with citizen science data and double machine learning. Citizen science projects are collecting increasing volumes of data around the world every year. Our goal is to use this data to estimate species trends. There are two key challenges. The first is confounding. Because most citizen science projects collect data opportunistically, changes in the data can reflect changes in the observation process, which can introduce bias. The second challenge is spatial variability. Local scale trends can vary across broad extents as the drivers of population change can vary geographically. And we're interested in trying to capture this variation. To illustrate these challenges, we're going to look at data from eBird, a global citizen science project that collects bird observations. eBirds become popular in part because individual participants can decide where, when, and how to conduct their survey. And this has led to a lot of changes over the past 20 years. These maps show data density by year in Eastern North America. And you can see that there have been substantial changes in the coverage across this period. These plots show the density of the time of day when surveys are conducted, colored by year. And they also show substantial variation across the years. How participants have searched for birds has also changed as knowledge and tools have improved. So where, when, and how people have searched have all changed, and this means that confounding is a real concern trying to estimate trends. The analytical challenge is to separate these changes in the observation process from those in the species population. The response model captures intra and interannual changes in species population. The response is Y. We'll assume that this is species counts, though it could be occurrence. We're going to model this as a function of two different components, intra and an interannual variation. We're going to let beta x be the term that describes the effects of features x that describe intra-annual variation and count. This could be geographic variation associated with habitat or environmental resources. It could also be variation associated with characteristics of the observation process, like search effort. The second term, tau t, where t is time, or the survey time in years, describes the interannual variation. This is our trend component, and the goal is to estimate parameter tau, which describes the annual rate of change in abundance. Propensity scores provide a solution to the confounding problem, the ability to separate population change and observation process change, by introducing a second model that keeps track of the change in the observation process. This is done by framing these changes as the dependence of time, here our response, on features x, and then uses this information to adjust the response model. This provides a solution to the confounding problem. Now let's consider spatial variation in trends. House finch is a broadly distributed North American species. The map here shows estimated trends across North America for house finch over the past 15 years. The eastern population is increasing in blue, recovering from an infectious disease. This is avian conjunctivitis. Whereas the western population is declining in red, suffering from increasing temperature and drought. Analytically, our response model is not flexible enough to capture the spatially varying trends. A straightforward solution is to include interactions with other features, like climate or disease prevalence. This can also be considered as a spatially varying coefficient model, where tau itself is a function of other covariates or other features. Now let's see how double machine learning puts these together. Double machine learning is a recently developed statistical framework designed to deal with these challenges. It extends the response propensity score models to feature-rich settings by considering the three components as non-parametric functions. This first one, the SDM of X, describes the effect of intra-annual feature effects. Again, this would be habitat or search effort. Tau of W describes trend effects of trend features W. And the propensity score model is a function of features X. Double machine learning is useful because it also provides a way to solve these two equations simply as three separate prediction tasks. And this can be done with generic machine or statistical learning methods: random forest, boosted trees, lasso, penalized regression, deep learning, or ensembles of these. One of the important innovations is that it allows these methods to be used while providing guarantees that the regularization or shrinkage bias associated with them goes away. A very interesting aspect of DML is the asymptotic normality of the estimator for tau. I want to show you, so this provides a really high-level kind of overview of DML. I want to give you a feel for how it works through our simulation study. When we apply it to eBird, we're applying it in a setting where we have a feature-rich setting. We use 78 features for X, describing geographic features, land, water cover use and cover classes, elevation slope aspect, weather. We also included a set of features that describe observers, search effort, and characteristics of the observation process. Including these in the propensity score model means we can account for potential confounding sources of interannual variation in search effort, search efficiency, and site selection. We've also included a large set of features in the set W to describe potentially complex spatial patterns of population change. To evaluate the method, we've constructed a simulation study. To simplify, the study is designed to replicate realistic aspects and challenges of analyzing eBird from the many different sources of variation involved. We've implemented the DML framework using random forest as the machine learning method for each of the three component models. We've applied this species by species. Here I'll share results from two species, wood thrush and long-billed curlew, that have different data sizes and data density to give you a feel for how this works. We're going to focus on the ability to estimate spatial variation and trends. The first set of simulation scenarios look at spatially constant trends. Blue is increasing, red is decreasing. This is the simulated map of the trend showing a spatially constant decrease. and an estimate that matches the direction and magnitude of the simulated truth. This is an example of a spatially varying trend. You can see that the simulated truth is replicated fairly well in the estimate, capturing the regional patterns of variation as well as the magnitude. These are 2 scenarios out of 10 that form the simulation study. It's been replicated a number of times. Here we share summaries showing the correlation between simulated truth and estimate. It does fairly well for wood thrush, a data-rich species. Long-billed curlew, the data for this species are much weaker, less data volume and less data density. The 2 scenarios that we were looking at before for spatially constant and varying patterns are marked in green. You get a sense that this model still, for this species, still a fair amount of information, but performance has declined compared to wood thrush. So to conclude, double machine learning has a lot of potential for dealing with these 2 challenges: capturing spatial variation and trends while controlling for confounding sources of variation. Challenges include practical implementation for propensity score, its evaluation, and estimating uncertainty in the face of temporal and spatial correlation. If you're interested in more details, please check out our archive, preprint, and you can see examples at the following link. Thank you.
Time for one question. Let's go ahead and move to our next talk. Alison Binley will be presenting on redistributing resources from monitoring to action, quantifying the value of citizen science data in conservation.
Hi, 2 minutes before the end, I'm going to show you. Okay, so I'll put on a timer so I can keep pace, otherwise I'm all over the place. Thanks. They're not up there yet.
Great. Hi, everyone. I'm Allison. I'm a PhD candidate at Carleton University studying with Dr. Joe Bennett. I'm just at the end of my PhD, actually. And this is a chapter of my PhD research, which looked at how we can kind of balance biodiversity monitoring and implementing conservation action using community science data. This I don't know if it died. There's only so many buttons to press.
Actually, it was working. Just advance this.
Working now? Okay. Glad it's not just. No worries. There we go. Yeah, so before I dive into it, I just want to acknowledge and thank my collaborators and co-authors on this project, as well as the agencies that are funding this work. And I also want to acknowledge that where I conduct my research in Ottawa is the traditional and unceded territory of the Algonquin First Nation. So there's a trade-off in conservation science between collecting information and actually implementing action. Biodiversity monitoring is obviously very important for informing which action would be best and will be most beneficial to biodiversity. But it's also less often acknowledged that monitoring is in itself an action. And so when we choose to conduct monitoring, in some cases, we're also choosing to delay action. And this in itself is a choice that can affect the outcomes to biodiversity. And so one solution to this dilemma is to make use of data that's already readily available and freely available. And the data source that I'm going to focus on today is community or citizen science data. I'm not going to spend a lot of time explaining what this is because I think we've had a pretty good introduction from Ali Johnston and Daniel Fink just now. But the logic behind my study is essentially that if we can use this freely available data, it may allow us to redistribute some of the funding that we have for conservation from monitoring to action. The idea being that if we can spend more money on implementing action, this might have better biodiversity outcomes. However, if we assume that professional monitoring data is of higher quality and can help us make better decisions, then it might be worth the investment, and we might actually be able to get better results this way by going out and taking the time and spending the resources to collect more data. And so the objective of this study that I'm going to present to you today is basically trying to assess the trade-offs between using community science data and professional monitoring data and what the outcomes are for biodiversity. So to explore this question in more depth, we used a case study, which was the Bird Returns Program. If you're unfamiliar with that program, it's run by the Nature Conservancy, or TNC, in Central California. Essentially, the goal of the program is to create pop-up wetlands by paying farmers to keep their rice fields flooded during spring migration and fall migration to benefit shorebirds as they're passing through. And so I used real data from this program. This includes the real costs of monitoring that were incurred by TNC when they were sending out professionals to count the birds and figure out where they would best spend their money on enrolling farms in this program. We also have the real bid values. So how this worked is there was a reverse auction process where farmers could basically bid the amount that they would need to receive in order to offset any costs on their end for keeping their rice fields flooded, so things like affecting their productivity in the season. We also had the real properties that were actually enrolled in the program as well. And so again, what we wanted to try to assess is whether if we could use eBird community science data to conduct prioritizations and decide which farms we wanted to enroll in the program, does this result in better outcomes for biodiversity than using the professional monitoring? Now, in an ideal world, we could pay all the farmers who want to be involved in the program, but when we're working with limited budgets, that's not always the case. And so we're using these different data sets to decide which farms we can enroll. So a lot of this work was building off of a previous project that was conducted by Robinson et al. And so in his paper, Robinson built these models that predicted the probability of detecting 7 different shorebird species across the study area. And so one of those models used only eBird community science data. The other used only the professional TNC or the Nature Conservancy data. And then the third model used an integrated data set which used both of them. I'll be referring to these throughout the presentation as the predicted values. Now, we use the predicted values to conduct our prioritizations, so essentially to decide which farms we wanted to enroll in the program based on the probability that the shorebird species would be detected there. And to do so, we used an R package called Prioritize R, which was developed by Hansen et al. This package basically just aims to maximize the biodiversity while also minimizing the costs and staying within a set budget. So since we work with a variety of different budgets in conservation, we looked at a range of them for these prioritizations. So conducting a different prioritization at different budgets, and we increased the budget incrementally until there was sufficiently enough money available to enroll all farms. So we're looking at the entire range of budgets that are possible here. Importantly, we also implemented a monitoring penalty for the professional data. So all this means is that when we have a certain budget for a prioritization, when we're using the predicted values from the professional monitoring data set or that model, we deducted the real cost of monitoring that was required from the overall budget that was remaining. Now, the main goal of the study was actually to compare the professional monitoring data to the community science data, but because we had this integrated model, and Robinson et al. In their study found that this one actually performed best out of all three, perhaps unsurprisingly. We wanted to also explore this as an option for conducting prioritizations as sort of the best available information. So we also included this one. And because this was our best available information, we also used this as a gold standard approach to assess how well each of the prioritizations performed. Now, to account for some of the uncertainty and whether the species really would be detected there, according to the model, we adjusted the values using Bayes' theorem based on the model sensitivity and specificity. So essentially, we're using the integrated predictions, but actually trying to figure out what the probability of detecting a species on a survey would be, conditional on whether or not the model predicted that they would be detected there. I'll be referring to these as the expected values. And when we're looking at assessing the performance of a prioritization at a given budget and using a particular data set, the biodiversity value would essentially just be the sum of all the expected values across all of the farms that were selected by a given prioritization. And so we had a number of different predictions when we started this study. Because there was the monitoring penalty and the eBird data was freely available, we intuitively expected that at lower budgets, the monitoring penalty would eat up way too much of the budget, leaving very little left for action. And this means that the prioritizations that were conducted based on the eBird data and the eBird predictions would perform better at lower budgets. However, we expected that because the TNC surveys were conducted on the farms that were where we were prioritizing our action, that they might provide better quality information. And so as the budget increased, we expected that it might be possible that the TNC data would be more valuable and result in better biodiversity outcomes. However, we did not find this to be the case. So we actually found that the eBird prioritizations performed better and produced a better outcome for biodiversity across the entire range of budgets. So the plots that you see here, on the x-axis, we have increasing budget, and on the y-axis, we have the difference in biodiversity value as a percent difference. And so what we did is we took the difference between eBird and the professional monitoring. So positive values imply that the eBird prioritizations performed better. Negative values imply that the TNC prioritizations performed better. The dotted blue line, if you can see up there, is at 0. So you can see that, in fact, the eBird prioritizations were outperforming TNC across the entire range of budgets. So just to reiterate, at no point did the professional monitoring outperform the community science prioritizations. And the point where the line kind of tapers off at 0 is essentially where the budget was just high enough so that you could enroll all of the farms. And of course, prioritization isn't necessary at that point. If you can afford to pay every farmer, you no longer need to be particular about which farms you're selecting. Interestingly enough, when we compared this to our gold standard as well, we found that the eBird prioritizations also performed pretty comparably to the integrated model. So even though in the Robinson et al. Paper, they found that that model outperforms the community science model as far as accuracy and sensitivity and specificity, in terms of informing decisions, they were quite comparable in a lot of cases. And so to summarize, when we actually do assess the difference in informing decisions between the professional monitoring data set and the community science monitoring data set, when we're accounting for the cost of collecting the professional monitoring data, we found that the community science data was the better option. I want to also mention that this is just one case study and this hasn't been examined across a bunch of different scenarios, but this is what we found for the bird returns program. So data quality is something that comes up quite a bit when we're working with community science data. And in particular, if you've read any of the other work on eBird, there's a lot of comparisons in trying to reproduce the exact same metrics of biodiversity, species richness, species abundance, or trend. But the data that's required for informing decisions can be a lot less intuitive. And so we just basically need what's good enough for us to make the best decision. And that's not necessarily the data set that's the most precise or the most accurate. Also, obviously, logistical constraints come into play as well. When we're looking at things like cost and actually introducing budgets into the conservation planning, this can have a huge influence on our results. Another thing that we didn't or couldn't account for in this study was that another advantage of using community science data is that it's readily available. And so there's a time lag associated with collecting data that can be really detrimental to conservation efforts. And so an additional benefit would be that we have this data readily available. However, I also want to say that professional monitoring is really important and necessary in a lot of cases. For example, if we're trying to assess the efficacy of conservation action, in a lot of cases, we might have to send out professional surveys. So the point I want to leave you with here is like, not that we can abandon all professional monitoring, obviously, but in a lot of cases, if we can find readily available data sets and work with those, it can be really beneficial. So just to wrap up, in conclusion, we did find in this case study that redistributing money from monitoring to action did result in better outcomes for biodiversity. And that gathering data isn't always necessary to make the best decisions, and more importantly, that it can be actively detrimental to the ultimate biodiversity outcomes. Thanks, I think I'm out of time. So if anyone has any questions, feel free to ask now or follow up with me afterwards. Thank you.
Hi, thanks. Is that on?
I can hear you.
Yeah, okay. That was a really interesting talk. I had a few things I was thinking about, but so there, the data that you're using from eBird, were you just basically using everything, or did you have some process for filtering? Because I guess you could get even better outcomes by only using parts of the data that are more reliable.
Yeah, so most of the modeling heavy work was done by Oren Robinson beforehand, and he did do filtering to kind of match the structure of a more of a professional survey. Yeah, something I also neglected to mention is like when we're comparing, you know, the capacity of community science data in general to inform decisions, eBird is one of the stronger programs, in my opinion, for, you know, producing research quality data because of, you know, reasons that Daniel and Ali have already explained in quite a bit of depth. So, you know, across contexts and different programs and different species as well. I work with birds because there's a lot of data for birds, but, you know, if it was mosses, I'm sure that someone might have a different opinion about that. So yeah, it really matters for sure, the different data sources and how you treat them as well.
Okay, well, let's thank Allison again for her talk. And our next speaker is Annabelle Stanley, who will be presenting on making informed decisions for private lands conservation under uncertainty and spatial complexity, a case study on the Northern Bobway.
Try it. Okay. 2 minutes before the end, I'm going to show you this. Could you do 1 minute? 1 minute? Okay.
Hi, everyone. My name is Annabelle Stanley. I'm a graduate student at the University of Georgia. I'd like to take a minute and thank my co-authors and advisors for all their help with my research. And I'm going to be presenting my graduate research, Making Decisions for Private Land Conservation Under Uncertainty and Spatial Complexity, a case study in the Northern Bobway. So I'd like to start off by talking about agri-environmental schemes. These are programs typically run at the federal or state level that take conservation dollars and put them into the landscape by enrolling private landowners to try and get conservation outcomes. And so the way they do this is typically with cost sharing or grant approaches. And so an example of this is the Northern Bobwhite. The Northern Bobwhite is familiar maybe to some Europeans as the partridge. It's the American equivalent at least. And the bobwhite has declined by 2/3 since 1980. And so we have this declining grassland bird species whose main habitat is found on private lands. It's in very sparse areas across the United States. And so agri-environmental schemes have been created explicitly for the species, which is one of the reasons we focused on it as a focal species. The other reason is that it's got agri-environmental schemes that have been the other reason is that it has population data and it's been well studied. So I'd like to start off by talking about decisions in agri-environmental schemes. The example landscape has 4 different private landowners that are eligible for enrollment, 2 are not eligible. And so you have 4 different landowners to choose between. In real life, this example is scaled up. And the decisions get complicated when we consider conservation practices that can be applied to the landscape. So examples here include burning and thinning. And so the decision maker not only has to choose between which private landowners they're going to enroll in the program, but also consider the conservation practices that are applied as part of the program or that the private landowner is offering to implement on their landscape. And so the research I'm trying to conduct is looking at 2 different approaches for enrollment across agri-environmental schemes. First, we have a model-based approach that uses optimization, explicitly considering the biology of the bird in its implementation. And the second is the status quo approach that uses a ranking framework. And so we use the northern bobwhite as a focal species here, considering which approach results in the most abundance of birds. So to set up this comparison, we start off with the different private landowners across the landscape. We then identify where the different forest stands are across the landscape, reduce these to forest stands that are specific to private landowners and impose a size constraint. We then randomly assign conservation practices across the landscape. And an important assumption to note is that we're assuming when we implement conservation practices, we have an increase in habitat quality, which results in an increase in bird abundance. To make this comparison work, we use an individual-based population model that we run for 30 years that includes habitat quality and habitat distribution as inputs. So to start off with, I'd like to talk about the ranking framework. The ranking framework, or the status quo approaches I use globally, considers a number of different attributes as part of a decision that the agency makes. And so attributes include locations, land use, and the actions themselves. Each of these are assigned points. The points are then tabulated for each of the different stands available for enrollment, and the highest points are selected. Underneath my framework, I then run this through the population model to get an estimate of abundance. And it's important to note that the attributes in different ranking systems are implicit models. These are things that the decision maker has identified that they care about, but they're not explicitly being monitored. And so that's where the difference in framework comes between the ranking approach and the model-based approach that I'm presenting here. So under the model-based approach, we're using optimization to consider all the different stands available on a landscape. These are binary because we're using a genetic algorithm. And so across these different examples here, we can see that the best solution would be solution 3 because we have the highest population. A genetic algorithm has been selected as the optimization tool here because we can use landscapes and it considers spatial processes. And so under this explicit approach, we can compare the optimization approach versus the ranking approach. So we start off by identifying the different private landowner boundaries. We then identify the forest stands. And this is where the 2 approaches differ because they select different forest stands for enrollment. And then when we apply the population model, we can see in the blue dots the final location of the focal species, and we can see that we have a high population coming from this optimized approach. And so when we do this across a random sample of landscapes, we can see 3 different things happening here. First, we have the comparison between the model-based and the ranking approach. These are in the open versus closed circles. Second, we have 2 different landscape sizes here. We have a small landscape at 26.3 square kilometers, and a larger landscape at 52.6 kilometers squared. And then finally, across the 5, 10, and 20%, these represent different amounts of landscapes that have been, different percentages of the landscape that have been enrolled. And so starting off at the 5%, we can see in the smaller landscape, there's not much of a difference between the 2 landscapes, between the 2 approaches. But then at the 5% in the larger landscape and at the 10% of both landscape, we see an effect and there's a difference between the 2 approaches that then diminishes at the 20% because these 2 approaches, because the amount of land available has been, the habitat has been saturated. And it's important to note that at the 5% of the larger landscape and the 10% of the small landscape actually are the same amount of habitat that have been enrolled. And so, well, we have the same amount of habitat being enrolled and the habitat quality has been increased in both of these landscapes. We actually see there's more efficiencies in enrolling 5% of a larger landscape. And so to conclude, I presented a framework today that includes bird biology explicitly, unlike the implicit ranking approach, because we have the population ecology as well as the landscape ecology under consideration. And we can see there are efficiencies in including this approach over the status quo ranking framework, at least at certain percentages of the landscape and certain landscape sizes. If we consider the scale effect here, which is incorporated in our population models, as presented at Yeiser et al. In 2021, scale effect essentially identifies where in the landscape an individual is and the quality of its habitat around it. And the northern bobwhite, noted in tan coloration, has a fairly large scale effect, which is likely why we didn't see a significant difference between approaches at the smaller landscape at 5%, whereas if we had a species of a smaller scale of effect, that percentage of land being enrolled could have been significant. It's also important to consider the larger decision context here. If we're implementing restoration across a landscape using agri-environmental schemes, we want those conservation dollars to be efficiently utilized. And the two frameworks presented here could be compared in the consequences stage of the PROAC cycle. I'd like to take a minute to thank the Georgia Corp unit for funding my travel, as well as all the different bobwhite co-managers who have spoken to me and informed my research. Thank you. Are there any questions?
So we have quite a bit of time for questions.
That was really interesting. Have you thought about how to address uncertainty in the decision model?
Yeah, so I guess we're hoping that if you implement a decision, the model that includes the population model explicitly, and we can at least run a sensitivity analysis to identify the uncertainty resulting in the model. And by using the model-based approach, we can take steps to implement monitoring to reduce uncertainty. So uncertainty could be addressed by the model-based approach, unlike the ranking approach. Does that answer your question?
How do you want to address the uncertainty?
So the uncertainty in the decision question or the uncertainty in the model framework? Sorry, say it again.
How do you address the uncertainty in the predictions?
In the predictions?
Yeah, within the decision.
Yeah, so we're planning to implement a sensitivity analysis for the population model, and that will address or at least indicate whether the decision is sensitive to uncertainty in the population model. And the uncertainty around scale of effect is something that we can work to address through monitoring efforts.
Okay, so in the absence of other questions, our final talk has been delayed until tomorrow due to some travel difficulties. So let's thank our speakers one final time and get some coffee.
We have a 15-minute break, 10-minute break. Thank you. Thank you.
Thank you. Yep, hold on.
Du PowerPoint. J'ai
Ouais, mais
aussi un
on a-
PDF.
J'ai une V1.
C'est pas grave.
je peux pas enlever le nom.
Kylian, tu dois être co-host. Then bien. Il y en a un là-haut qui m'a dit qu'ils n'entendaient pas très bien le dernier talk. Je ne sais pas si vous comptez là-haut, le dernier rang. Ah oui. Mais bon. Ah merde. Il y a plein de place en bas.
Good afternoon. Yeah, sorry for the delay here. So our next talker will be Euring2023, and he's going to talk that sonotype as a novel insight into the Congo Basin rainforest dynamic. Yeah, welcome.
Thank you. Hi everyone, my name is Euring2023 from DRC, the Democratic Republic of the Congo. My work is bat sonotype as a novel insight into the Congo Basin forest dynamic. For a short background, I'll talk about the context, and next about the research questions and the main results, and after a short conclusion. What is the context? In many parts of the world, bats are considered as bioindicators, but bat populations are declining in many parts. And in the Congo Basin forest, significant efforts have been made by various studies to understand functional characteristics of bats in relation to their habitat. But most of those studies are focused on mist netting. And those techniques or methods have some inconvenience. It's like they are invasive methods and they are time consuming, the risk of infections, and also there is no efficient sampling of open habitat, higher canopies, and species that are sensitive to mist nests. And through this study, it was wondering to some question. It's like, what is the relationship between bats functional group and habitat they colonize? And secondary question, what is the three species that the sporas can be disseminated by frugivorous bats? The second is, what is the influence of forest habitat structure on bats' activities? And at last, what phenotype that can be identified based on the analysis of echolocation calls of insectivorous bats. And for the method, this study was conducted in the Yangambi Biosphere Reserve, which is located in the Democratic Republic of the Congo. And for the method, we used to establish prevalence plots, and also we did inventory of trees, shrub, and liana with diameter of breast heights, which is superior to 5 centimeters. And also we did a description of habitat in subplots. For invasive, non-invasive sampling of bats, we did a capture, making recapture, and we use mist nets and app trap, and we had 3 capture sessions from 6 p.m. to 6 a.m. Also, we did acoustic surveys in passive acoustic, in passive mode, and we used 2 types of recorders, audiomorph and anablat. And acoustic recording was performing in continuous mode from 6 p.m. to 7 a.m. And we had in a total 306 hours of acoustic recording at a sampling rate of 340 kilohertz. And for data processing, we use the Kaleidoscope Pro software to convert audio files from WAV file format to zero crossing. And also we used the analog W to extract, to filter data, also to extract code parameters, and also to identify bat species. And also we use the R software to modelize the bat activities with meteorological parameters, including temperature, air, humidity, and habitat structure. Also, we use the software to visualize the similarity between calls parameters. And at last, we use machine learning to classify bat echolocation calls. What are the main results of these studies? We have captured 42 individuals, including belonging to 4 families and 3 species, with an abundance of frugivorous bats. And also, by this study, we were able to inventory that 16 tree species have been disseminated by bats, by frugivorous bats. And at last, acoustic survey allowed us to identify 11 insectivorous bats. But there was a large amount of data, and we couldn't identify all species that are in the forest, or there is no co-library in the region, so it was difficult to identify all species that could be in that forest. And what is the conclusion? The last result is that a medium to higher density of the understory and a medium opening of the canopy have a significant influence on bat activities and call structure. And to conclude, complementarity of monitoring and capture, mark recapture, allows us to inventory more species, mega and probats, than each technique separately, but also to highlight functional role. I can cite pollination, dissemination, and insect control of these different group species. Thank you for your kind attention.
Thank you very much. We have time for a couple of questions.
Thank you very much. Such a nice talk. So you detected 13 species with misnetting and 11 species with the sonotype.
Yeah.
How many of those were the same species?
Okay. For the 11 sonotypes, there are only insectivorous bats. Only insectivorous bats. And only 5 were identified by the acoustic survey and were also captured by misnets. Yeah.
So that's a big gain. That's great.
Thank you.
Thank you.
Yeah.
But you do have a way to go in detecting species, because I think you told me that there's 1,000 species of bats in isn't it? Or we talked before and you said that there were 1,000 species of bats in your country, isn't that right?
Yes. I work in lowland forests. Congo is a big country with different ecosystems. There are some species that you can find only in the lowlands forest, others are in the mountain forest. So my study was in only the Yangang Biosphere Reserve, and in that forest, that region, there are not so many bat species. Yeah. And also bats, there are 2 groups. There is frugivorous bats and insectivorous bats. For the acoustic sampling, it's only focused on insectivorous bats. And in that region, as I said, there are so many bat species, but it's very difficult for us at this time by acoustic survey to identify all the species, because we don't have any core library in the region that can allow us to compare our acoustic recording and what the other have been done. Okay, that is the first challenge. And the second, I didn't do the sampling in the whole region of the lowland forest. Yeah.
Thank you very much.
Yeah. Thank you.
Thank you. Our next speaker is Philip Patton with colleagues, and they're talking about the effect of fully automated photo identification on mark recapture. Yes.
Hi, everyone. First of all, my co-authors would like me to tell you that these affiliations are incorrect, so don't pay attention to those. Kind of the motivation here is that one of the primary goals for my dissertation is to assess a stock of spotted dolphins that live in Hawaii. But in order for me to do so, I have to go through this giant stack of photos and identify all the dolphins in those photos if I want to do any sort of like photo ID-based marker capture. But I don't want to do that, so I'd rather use an algorithm to do so. And there's a lot of these algorithms being released every year, as shown by this graph from a review article that came out last year. This is kind of the state of the art. This came from the first chapter of my dissertation. Here we're looking at the performance of kind of one of these new multi-species photo ID models across 25 species in 40 catalogs. And what you'll notice is that there's just a ton of variation in performance among species and even among catalogs for species that have multiple catalogs. But this only shows whether or not the model got the prediction right or wrong. In terms of capture recapture, we're kind of interested in what types of errors the model's making. For instance, it could be falsely rejecting matches. That is, the individual is actually already in the catalog, but this is saying, but the model's saying it's a new individual. Or it could be falsely accepting matches, essentially confusing two animals. This is also known as a band read error, or I guess like a ring read error. So if we look at those same 40 catalogs and break it out by the photo, the error type, and look at the rates, this is the figure you get. And you'll notice if you look at this long enough is that for this model and for a given catalog, it's more likely to falsely accept matches than it is to falsely reject matches. So after looking at that plot, I was wondering, okay, so if I use this model on my giant stack of spotted dolphin photos, generated capture histories that way, would I then be able to trust the capture recapture estimates that I got from that? And if not, is there some better way that I could deploy this model? For instance, could I use a semi-automated approach where I have the model just rank the most likely matches, and then some experienced user, that's not me, goes through and actually makes the choice about whether or not this is a match or not? And then, so I wanted to explore these questions in simulation and then in one example application. So for the simulation study, I'm trying to compare this fully automated scenario to the semi-automated scenario using pop-band models. Pop-band's a popular choice in the dolphin community. And I'm going to take the error rates from the catalogs and the plot that I showed you earlier using that model that we've been discussing. But these error rates are going to differ between the two scenarios in ways that I'll discuss later. So I simulated 100 of these pop-band data sets for these 40 catalogs in these two different scenarios. And if you want to see how I did that, you can go look at my horrifying code in this GitHub repository. So for the fully automated scenario, generating the error rates is pretty straightforward. I just have the model spit out its top prediction, and then I classify the prediction as either right or which kind of wrong, so false accept, false reject. And in fact, that's the plot that we looked at earlier. So these are the error rates for the fully automated scenario across the 40 different catalogs. Semi-automation scenario is slightly more complicated. Again, I'm trying to simulate this situation where the model spits out top 5 predictions, then some experienced user goes through and picks the correct match. So what I did is I had the model spit out the top 5 predictions, and if that label was in the predictions, then I said, okay, yeah, that's a match. However, or if not, then I rejected the match. So I, again, trying to simulate the situation that this is an experienced user doing this, I set a low fixed false accept rate of 2% across all catalogs. This kind of came from looking at the literature and also discussions with my co-authors, but we'll talk about that a little bit later. As a result, many of these false accept errors get allocated to false rejects. And so in essence, in the semi-automated scenario, the false reject rate just tends to be a little bit higher for a given catalog. And finally, to set up the pop-band model, I set the number of cases to 10, the parent survival rate at 0.9, and the initial entry probability at 0.35. And to try to add a further dose of realism, I let the superpopulation size and the probability detection vary by the catalog using information in the catalogs that I was using and some rules. And we can talk about the rules if you're interested, but what I want to take away is that the populations end up being small, so like less than 2,000 individuals, and the probability detection tended to be low, so less than 0.5. And then I estimated phi and the superpopulation size using PyMC. And here are the results. On the x-axis, we have the estimate of phi. On the y-axis, we have the catalogs. The color, or each dot represents the point estimate of phi from each one of the replicates. and the color of the dot is the false accept rate from the catalog. And the dashed line shows the true value of 0.9. And what you'll see is that there's this kind of strong relationship between the false accept rate and the bias and the negative bias in phi. Get all the way up to that disgustingly high value of 0.4. The relationship is a lot less clear with the false reject rate. These you can see is just kind of all over the place. So it doesn't seem to be necessarily driving that bias as much as the false accept rate. And now comparing the two scenarios, we have the semi-automated scenario in blue and the fully automated scenario in orange. And as you'll see that the semi-automated scenario tends to remove a lot of that bias, which makes sense if there's a low fixed false accept rate, and that's what's driving this bias. Okay, now on to the example application. This comes from a photo ID survey off the west coast of Oahu looking for spinner dolphins. This was done in a robust design by my colleague, Leah McPherson. She went through those photos herself. She likes dolphins, and so she identified them that way. I used an algorithm to do so. The model or the algorithm does really well in her photos. It tends to agree with her a lot, which will explain the results. And then I compared, so I basically generated those two different capture histories, estimated the superpopulation size in phi using those two different ones, using OpenCR package from Marie Efford. As you'll see, the estimates are functionally identical, which is not surprising given the amount of agreement between the model and Leah when it comes to APs. So in conclusion, from the example or from the simulation, the simulation suggests that at least for these data, or in these catalogs in this model, that semi-automation is kind of the way to go if we want to do some capture-recapture, or capture-recapture modeling down the line. Sadly, that's what I'm probably have to do with my spotted dolphins. But this conclusion really rests on this low fixed false accept rate, which in talking to my co-authors, it's probably going to vary by user, so the user experience, individual animals, obviously two animals might look alike given their marks, and then also some species. Some species are really easily identifiable, while others are, less distinct. And then I also didn't look at the trade-offs between the labor costs and the bias in the estimator, which will obviously differ. And with that, acknowledge these great folks, especially shout out to the NOAA Quest Fellowship for funding my existence. And with that, I will take questions.
Thank you very much for an excellent talk. We have time for 4 or whatever questions.
Hi, very nice talk. With the model you use to automate the identification, you don't need to feed it with a known animal. It doesn't need to learn. It already knows with new animals to match them.
Yeah, so essentially the way it works is that it's been trained on this large data set. It was like 75,000 photos. So the way it's going to be deployed is that if you identify an animal, so ideally it'll feed into some database that will go into the catalog or whatever. But essentially it just estimates these similarity scores between photos. And then you have some kind of somewhat, not exactly arbitrary, but you have a threshold, whereas above this threshold, okay, these are the same animals. So say above 0.5 or whatever. And below that, you're like, okay, no, this is a new animal or something like that. So for this case, when I was using it to identify all the dolphins in the spinner dolphin application, what I did is I just basically built a network essentially. So photos were connected, that's the same individual. So connected by the similarity score being over 0.5, if that makes sense.
No other question. There is no question in the chat either. So I think we go on. Yeah. Thank you very much. Okay, our next speaker is Gaël Barbon and a whole bunch of collaborators there who will talk about FID, unfolding the potential of deep learning for radio frequency identification. Welcome.
Okay. Okay. So, hello everyone. I'm Gaël Bardon. I work at the Scientific Center of Monaco. So, I'm a PhD student. And I will present you how we unfold the potential of deep learning for radio frequency identification, or RFID, using a workflow named RFID. So RFID monitoring systems have been widely used for the past decades to better understand animal population with studies of population dynamics using the CMR frameworks, or for example, in studies of behavioral ecology. And it was used for many different taxa, including birds, mammals, fishes, or even invertebrates. But what is radio frequency identification? So it's a system that allows monitoring of uniquely identified individual using passive integrated transponders, so PIT, that are passive, so they have no battery and theoretically an unlimited lifespan. So they are attached to the animal by being either subcutaneous or attached to a leg band, like for example with the Bluetooth here. And when an individual is equipped with a PIT, it can be detected with antennas that can be installed, for example, at the entrance of nesting box. So it presents a lot of advantages and challenges because it allows the record of a vast amount of detection for individual lifetime and for potentially many individuals. And it's a fully automatic system so that it doesn't require recaptures. But we have to wisely choose where to install antennas to a fixed observation point, for example, at narrow entries of breeding sites, perches, or nesting box. And it's far from possible missing detection because the detection range is limited to a few centimeters to 1 meter according to the system. And there is the impossibility to detect multiple tags at the same time with the same antenna. So the aims of our study was to infer individual behavior from RFID detection using a deep learning workflow that we name RFID and the software named Sphenotron. So one of the main challenge was to take into account technical limitation of RFID system and the biological variability by developing RFID-specific data augmentation steps. And we also aim to use visualization tools to better understand and open the deep learning black box to check how our models detect biological features and make their decision. So we based our study on the king penguin monitoring system in Crozet Archipelago, where 15,000 king penguins were tagged since 1998 in the closed area with only 3 pathways between the sea and the colony. And we installed 2 antennas at each pathway to record the penguins and that direction. So it allowed us to have 7 million detection in 2022. And for individuals that reproduce in this closed area, we can observe stereotypic patterns using the software Sphenotron. So here, with the view of the Sphenotron, we can see in orange the period in the colony and in blue the period at sea for one individual. And we can easily interpret and determine what is the breeding status of the bird, what is the breeding outcome, so if it's a success or a failure, what is the sex of the bird, and what is the breeding date, so the start date of the breeding. But we wanted to do this automatically because we had lots of individuals. So we use convolutional neural networks that were classically used for 2 dimensions for photo identification, but that exists in 1 dimension. For example, with bird vocalization classification that you may know in the application BirdNet. We wanted to mimic the expert interpretation to classify breeding season. So for one individual, one season, we wanted to know the breeding status, the breeding outcome, the sex, and the breeding date. So we built a workflow that I will explain you. For the first part, it was data preparation. So we had to transform our data to provide a readable format for analysis and for the CNN models. So we divided the breeding season in 12-hour periods, and we created two vectors, one for the location of the bird and one for the number of detection for each period. And we associated 300 of these vectors with field observation of the breeding status, the breeding outcome, the sex, and the breeding dates to build our training or ground truth dataset. Then we had the model development. So for the CNN model architecture, we started from classic and simple one, and we added layers through trials and errors using our training dataset that was divided in two parts, one part for training and one part for validation. We then added two steps of data augmentation, one by removing soft RFID detection at each epoch of the training to mimic the missing detections that occur in the field, and one by shifting the cycle at each epoch of the training to mimic the phenological variability. And then to estimate breeding dates, we added a post-processing step by training a model to determine if a cycle starts at the right breeding date. And we use the probability given by this. And finally, we use visualization tools to highlight the part of the breeding cycle that are used by the models to make their decision and the classification. So here with two examples with the blue curve. So these are activation maps that show where in the cycle the model looks to make the decision. And at the bottom, we can see all cycles combined. And we saw with this that indeed the models make their decision on the same parts of the breeding cycle than human to classify the cycles. So then we had the testing and deployment. So we test the classification using human expert classification of a sample dataset, and we reached really high performances. So we run the classification over all our cycles, which represent approximately 80,000 cycles, and it ran for about 2 hours. So we put this result in our database so that it is available in the 3.1 software. And here, for example, for one individual, we have the lifetime and the breeding status and outcome for each season with NB non-breeding season, failed breeding, and successful breeding. So I'd like to come back just on a few points. We had the blind detection of meaningful ecological patterns using the visualization tools. So it shows us that indeed the models make their decision not on artifacts, but on meaningful patterns. And it opens some perspective to maybe detect some patterns in more complex and bigger datasets. We tested with this workflow with another species, so the Adelie penguin, and we found also really great results. So we think that any RFID monitor species with stereotype movement during a given life stage could benefit from such processing. And it makes our datasets maybe more in line with the FAIR principle by better organizing, managing, and securing our datasets. And we think that it contributes again in reducing our impact on the studied population by limiting our presence in the field while continuously gathering breeding data to monitor the health of wild population. And to finish, I just want to show you two results that were made possible by such processing, with, for example, the age-specific breeding success rate for each cohort since 1998, and the phenology, so the breeding date of each bird for all years since 1998. Thank you.
Very much. That's fascinating work. Is there a question? There's no question in the. Sorry.
Hi, thanks for your talk. I was just wondering, do you have 100% detection for those individuals, or is there some possibility they can get missed?
We haven't 100%, but we are close. We run CMR model, and the probability is almost 1.
Okay, and does it account for the detection process, the model that you're fitting with the learning?
Sorry.
Do you account for the detection process in your model?
Yeah. We added a correction of missing detection, and we had an algorithm to detect where they are missing detection, and we correct them.
One more question.
You have multiple antennas, so you get the direction in or out of the colony?
Yeah, we have 2 antennas at each pathway, so we can infer the direction. But sometimes we have just one, so we can interpret and know that the bird come back from the sea or leaves the colony.
Thanks. Thank you very much. Okay.
Okay, thanks everybody. For tuning in. Hope you're having a great conference. Wish I could be there. So I'm going to talk today about some work that I've been doing along with my colleagues on estimating parameters from MODIS detection data. Many of you are probably familiar with MODIS. It's a large-scale automated telemetry network consisting of thousands of towers that can detect specially coded radio tags from birds as they migrate across continents or across hemispheres, like this painted bunting shown here. But analyzing data from MODIS is not easy, and I'll highlight some of the challenges and some of the work we've been doing on that in this talk today. So first, let's think about how we observe MODIS data. We tag a bird, we release it, we'll call that tagging point time 0, and then we track that bird over some length of time, and if we're lucky, the bird will be detected by towers as it migrates. So here are some hypothetical detection data where the points are detections and the colors are the bird's state. So in this case, orange is the bird on its wintering grounds, yellow is during migration, and green is on the breeding grounds. So this is in many respects capture-recapture data, and we can use capture-recapture methods to analyze it. And a good starting point for that might be discrete time multi-state models. So we can imagine binning up this study period into some temporal bins of equal length, keeping track of whether or not the bird was detected during each one of those bins and what state it was in, and then fitting the model using conventional discrete time methods. This approach has several different disadvantages, though. First of all, the bin lengths are arbitrary, and what length of time we decide to bin the encounters into can influence our inference, which is not ideal. Second, when we go to fit the model, we have to loop over all of these zeros that we added to the data, and that adds computational costs. Third, although not required, we oftentimes write these models in terms of latent states that we have to track, keep track of through time, which also adds computational burdens. And oftentimes, to avoid really sparse encounter histories, we oftentimes would make the bins relatively wide, but that not only limits the resolution of inferences about when state transitions occur, it can also lead to situations like this where a bird might be detected in multiple states within the same bin, and we have to figure out how to handle that when we go to analyze the data. So alternatively, we could treat this data as continuous time encounter data, where all we have to keep track of is the time between detections and what state the bird was in during those detections, and we can estimate parameters using continuous time models. The downside of that, of course, is that continuous time methods are less widely used by ecologists, and so somewhat confusing, but I'll walk through some of the aspects of continuous time models here. So just like any multi-state model, we have a matrix that defines transitions between states. In the case of continuous time models, though, these are not transition probabilities, these are instantaneous rates. Rates can vary over time, but I'll show them here as just being constant for the sake of simplicity. So this dead column here corresponds to hazard rates, so individuals transitioning from the live states to the dead state. So these can be state specific and allow us to make inferences about when in the annual cycle individuals experience the highest risks of mortality. The off diagonals here are transition rates between states. So in this case, from going from winter to migration or migration to breeding, we can set the other off diagonals to 0 to control what transitions are allowed and which ones aren't. Mathematically, the rows have to sum to 0, so we enforce that by setting the diagonals equal to the negative sum of the other entries in that row. And then the last row here corresponding to the dead state, we set to 0 because individuals can't transition out of the dead state. So using this intensity matrix, we can calculate the likelihood of detection, of transitions over any length of time by exponentiating this matrix times however much time passes between our detections. So that's a relatively simple calculation. Now, of course, with MODIS data, we have not only the state transitions occurring, but also we have to observe the birds at a tower. So we have to include that observation process in our likelihoods. We can do that by defining another matrix. This is just a diagonal matrix with the state-specific detection intensities on the diagonal. So you can think of these as just the expected number of detections over some length of time while the bird is in each state. And then we can incorporate that into our likelihood using this formula here. So with this matrix gamma defined for each of our detections, we can compute the likelihood of the encounter history for each individual. Now, like all capture-recapture data, from the last detection to the end of the study period, there's some uncertainty in the individual state. We can account for that uncertainty by just summing whatever the probabilities from this gamma matrix for whatever row the last detection occurred in, and that allows us to calculate the full likelihood for each individual's detection history. We can use this likelihood to then estimate parameters in the model using maximum likelihood or Bayesian methods. That's a little bit about how the model works. We've been applying this to a really nice MODIS data set that was collected by my colleague Nathan Cooper and Pete Mara from the Smithsonian Migratory Bird Center. They've been tagging Kirtland's warblers on the wintering ground with MODIS tags. I'll show this animation as birds leave the Bahamas in spring and are detected by towers during their spring migration to their breeding grounds in Michigan. So this is a really unique and nice MODIS data set to test out these methods with. Here's what the detection data actually look like. This is 134 individuals that were tagged over a 3-year period. You can see there's some annual variation in effort that we can account for in the model, but still a really nice data set for estimating these types of parameters. So we fit this model to the Kirtland's warbler data set. These are the estimated transition probabilities. So from winter to migration and migration to breeding, these are daily probabilities. So we can see the individuals start to leave the wintering grounds in mid-April. They've all departed by the end of May. They start arriving on the breeding grounds in early May, and they've all arrived by mid-June. So this corresponds really well to on-the-ground observations about when birds leave the Bahamas and arrive in Michigan. But it's really cool to be able to estimate these daily phenologies with such high temporal resolution. We also get state-specific hazard rates. These are the initial estimates we got out of this model. We see relatively low hazard during the stationary winter and breeding periods, much higher hazard rates during migration, which is what we expected. Though when we did some back of the envelope calculations, we realized that these hazard rates are much too high. They correspond to annual survival rates of like 10 to 20%, much lower than we know is true for Kirtland's warblers. So something was wrong with this model, and my colleague Scott Yanko sort of realized that part of the problem was that the way MODIS detections occur are likely violating one of the assumptions of this model, and that is that the detections occur at some constant intensity. So if the detection rate is constant, then we would expect the detections to be more or less uniformly distributed over time. But when we look at the MODIS data, we see that they tend to be really clustered, which makes sense. Birds are not near a tower for some period of time, and then they are near a tower and they get detected multiple times, and then they leave and they're not detected again. So this is kind of a hard thing to account for in continuous time models, but it turns out there's this class of point process models called Hawkes process models, where the intensity varies as a function of the detection history. So basically, when there's an event, in this case, a detection, the intensity jumps up and then it declines over time until there's another detection. And so we can allow the detection intensity to be a function of the detections themselves. And that turns out to be, I think, a pretty useful approach for MODIS data. So when we fit this model with the Hawkes observation process, we get much lower hazard rates. These seem to be a lot more in line with what we would expect based on survival estimates for this species. We still get about double the hazard rate during spring migration than during stationary periods, and it's really exciting to be able to estimate that. So a cool use of these Hawkes process models, I think. So I think there's still a lot of work to be done on these models. We need to think about things like model selection and goodness of fit. How do we distinguish between these alternative ways to analyze, to parameterize the models, as well as thinking about sort of the relative performance and efficiency that comes from using these continuous time models versus more familiar discrete time models. For Kirtland's warbler, we have this really nice scenario where birds are either all in the Bahamas or all in Michigan. We don't have to worry about migratory connectivity, but for most species, we're going to have to think about how we include more complex movement patterns into these models, which I think is an outstanding question that needs to be answered. As well as how we deal with other types of data. We get continuous time data from all sorts of new technologies, camera traps, pit tagging, satellite telemetry, and these approaches could be really useful for those data sets, as well as for thinking about how we integrate different types of data together. So with that, I'd like to thank my colleagues who helped with this work and the funders that made it possible. And with that, I will take questions.
Accepting my proposal for a talk. We have heard several talks today about citizen science and community science and so on. This is not a new thing, as you all know, but still I think it's an important part of how we monitor biodiversity in general. So this talk will be it's late in the afternoon now. This talk will not contain any equations, not many results, but I will mainly talk about the experiences we have of setting up such a program and how we sort of built this from the beginning. So in wildlife management and wildlife biology, participatory monitoring has a long history. For many of the harvested wildlife species, this has been quite a common way of monitoring their populations. Several state variables have been monitored in this way. It can be distribution, it can be abundance, it can be other aspects of phenology, life history traits, and so on. A couple of years ago, a PhD student in my group, Ben Cretois, did a systematic survey of to which extent different European countries have monitoring programs, either covering the whole countries or part of the countries, where hunters contribute, recreational hunters contribute with data. This data can be counts, it can be genetic or biological samples for genetic analysis, and so on. And as you can see, this, for the different types of species, this is happening in many different countries in Europe. Of course, the reliability of the data can vary widely in between the different programs, but it's quite a common activity. Community or participatory monitoring has many benefits in terms of both efficiency and stakeholder engagement. And of course, there are several pitfalls also in terms of conflict of interests and things like that. These type of participatory monitoring schemes, they can recruit participants from specific local communities in a protected area or something like that, but they can also recruit volunteers or citizens from specific user communities. And the one that I will talk about now has recruited from a specific user community, basically small game hunters in Norway that has a pointing dog. And they are contributing to surveying this, the game species they are hunting on. The program is called Hønsefuglportalen. It was established in 2012 as a collaboration between researchers, public and private landowners, national and regional environmental management authorities, and the National Hunter Association. And the main objective was basically to monitor grouse populations. So it's 4 species of grouse that are included in the program: the capercaillie, black grouse, rock ptarmigan, and willow ptarmigan. And the main motivation for setting up this program was to provide a basis for sustainable harvest management. Prior to this, I mean, of course, less so in Europe, in Norway, but in many contexts, harvest is a contentious issue, quite a lot of conflicts surrounding that. But prior to this program, there were basically no counts, no information at the local or regional level that could be used to guide harvest management. The program is crowdsourced. A large part of this, the program, is funded by national environmental agencies, but also the user groups contribute. The core of the program is a distance sampling line transect survey. So the field teams is basically made up of 2 persons and 1 pointing dog, and they survey along predefined survey transect lines, the same lines each year. So compared to, I mean, normal citizen science program, this is quite a bit more structured because we know the effort and we know where they are sampling for the birds. When they find birds, they will locate the GPS or the geographical position and also measure the distance to the transect line. And they also note down the sex and the age of the birds when possible to see that, and several other parameters along the way. They also report additional species that we know are involved in the population dynamics of the ptarmigans, like small rodents, for instance, which is in Scandinavia is very tightly linked. The drawback, of course, is that this is not the program that we were able to design from top. So it basically builds on local and regional initiatives. So we were not able to have sort of a structured, nice study design on a national scale. But in areas where they were interested in participating or there were already established surveys, we could challenge them to use common guidelines for local surveys. And they also use common field procedures and common field protocols. So we tend to see this as something between structured, call it proper monitoring, and citizen science. This floats somewhere in between. One key to succeed in collecting these data has been to set up nice infrastructure and tools that help us manage the program. In the beginning, we were using a web portal, and the field workers were reporting their data in the field in the web portal. But later, we have developed an app for mobiles, so that the regional contacts will assign different lines to the different field teams. And that's the lines that they have to follow. And they will register directly using their mobile phone. And we also get the track log to see to which extent they are following the lines and things like that. Over the years, we have also developed training courses and an exam for the field workers. The total effort has grown over the year. And currently, it's quite an impressive effort. Last year, close to 10,000 kilometers were surveyed. That's roughly 3,000 survey lines. And in the peak years, more than 40, close to 50,000 ptarmigans are observed, in addition to some thousand forest grouse. In 2022, Finland also joined the program. Yeah, so all the portal and the mobile app are translated into English and Finnish and so on now. So it's ready for also other users in other countries to use the infrastructure we have developed. An important part for us has been to share the data that is collected through this, as is common for most citizen science program, but not all monitoring and hunter-based surveys. So we share the data, at least from public areas, through GBIF using the sampling event model, so that all the metadata and information about the sampling process can come together with the observations. So you can use those to construct the distance sampling models or the other models that you think you will apply on this. Through other projects, we have also developed our code and our packages so that we can easily download them and run the standard functions we are using to report back, so that we keep it as transparent and open as possible. Yeah, this has all the way through been a close collaboration between management, landowners, and research institutions. And that has been quite an important part for aspect of this project. And we see that now that the landowners and the managers, they find great pleasure in seeing that the data that they collect for the management is also used for scientific research. And since the data is also shared on GBIF, they also find great pleasure in to see that a wide audience of researchers across the globe is using their data to assess a wide range of different questions that were not part of the original plan. Did it help for the grouse species? That's a difficult question. We think that the abundance has increased over the years since we started the program, but that's not the main. I mean, that there are many reasons for that, and creating the program was probably not the main reason for the increase. But what we have learned, at least, is that managing such a program is as much about managing people, as has been said previously today. Of course, it's challenging to keep improving the quality of such a program without creating change points in a time series that are difficult or impossible to model properly. And also we see that this close collaboration between research, management, and stakeholders is a prerequisite for a successful implementation of this. So you have to sort of work your way around problems that for sure are there. So that was a non-technical presentation of a data set that is freely available for use for distance sampling or whatever other analysis you prefer.
Thank you very much. We have time for one question. No, so I have a silly question. What software are you using for doing your big distance sampling analysis there?
For the standard, we are using R and the R distance package, but we have also developed hierarchical models in innovation, partly based on your rules. But Chloe will present a model that we're working on now in 2 days. So that will be the technical aspect of this sort of package.
Yeah. Excellent.
And that's based on, well, we're using Nimble for that part.
Thank you very much.
Okay.
Okay, our next speaker here is Philippe Supran, who's going to talk about modeling life cycle event phenology using biometrics collected by citizen science ringers. Welcome, Philippe.
Hello, thanks for hanging in there. I want to talk today about kind of a byproduct of market capture programs. And so this is data that is collected in schemes where the primary purpose of the schemes is to do market capture and to do demographic analysis down the road. But I would argue that having the animals captive provides a really good opportunity to collect additional data that can give us even more information than demographic analysis alone. And I'm going to focus on biometrics that allow us to make inferences about phenology, because phenology is a really powerful tool to understand what is happening within breeding seasons or within the annual cycle of animals. Whereas for most kinds of market capture analysis, kind of what happens within a year is a bit of a black box, and we're looking at year-to-year changes in vital rates instead. And there are these textbook examples of flowering phenology or egg-laying phenology that have told us a lot about how climate change affects living systems. And I will present some work, first off, why I think it's a good idea to study phenology in this context, and then also some statistical work of how to do that better. And so the main data type I'm talking about today is flight feather moult data in birds. And essentially that is a standard biometric collected in the British ringing scheme, in ringing schemes elsewhere in the world. And that's a pretty good proxy in passerines, at least, for feather moult in all of the bird, basically. And what we do for that, or what the ringers do for that, is they score the feathers on the wing by how far they've grown, and we can then sum those scores over the wing, and we can account for different sizes in feathers And we get like something like this approximately linear progress score of molt. And I think I missed a slide here, yeah. So this is this continuous score. We also can collect other types of data. So we could say the molt is a category and just kind of coarsely divide birds into old plumage, molting, new plumage, or one metric we also collect is the brood patch. And there's a key for different stages of the brood patch development. And if we're just interested in these categories, you can use ordinal regression to do inferences about phonology, and I won't really talk about that today, but I did a small review of various models some time ago. So yeah, the focus is these continuous scores, and the quantities we're interested in to draw inferences about is usually when do the birds start molting, what is the population variance or standard deviation of the start date, and then how long does it take for the birds to complete molt. And that's because that's how we understand how this fits into the life history cycle of those birds, and how it kind of governs conflict between different life history stages, and we can make a picture of what ultimately drives the vital rates then that we may observe in market capture analyses. And the model we're using for this is based on a model that Les Underhill came up with in the late 80s. And it's essentially, if you're familiar with censored regression models, it's essentially a Tobit regression model. So we have a censored linear regression model with a kind of linear likelihood. And we can use the old dates of old observations, dates of new observations, and can put categorical likelihoods on them. And typically we do that using a Gaussian model for the distribution of the start date. So this little ft would be the normal distribution function, and the big ft the cumulative distribution of the normal. And we did this for a population, or for the various populations of willow warblers in Britain. And Kat Morrison, who's here in the audience, did some nice demographic work on this species. And essentially what we find in Britain is there's a split in the population. The northern population is increasing, the southern is decreasing. And also from these demographic studies, we know that this is driven not only by better reproductive success in the north, but also a higher synchrony between adult survival and good reproductive success in the north. And so we were hoping that by looking at the phonology of the life cycle, we might better understand why reproductive success in the south is less good than in the north. And to that end, we analyzed brood patch data using a categorical model and the molt data using this Underhill model that I described. And to kind of very quickly summarize the results of that, so we have a phenological plot where on the x-axis you find an index of climate warming. So warm springs are the positive values, cold springs the negative values. And we're looking at 3 slices of the British population from south to north. And essentially what we find is phenological responses to global warming in different life history stages. So throughout Great Britain, we find that laying gets earlier and earlier as it warms, and that molt kind of is also gets earlier, but it gets earlier more in the south with warming than in the north. And the strongest response we found was in the phenology of this brood patch regression. And so essentially our interpretation of this data is that in the north, the birds are released from having conflict between breeding and molt in the annual cycle. So in the past, in these cold years, the refeathering of the brood patch would happen simultaneously with the wing molt. And so there's energy investments to be made in the bird's maintenance and into their reproductive success. And with warming, they can lay earlier, they can finish reproduction earlier, they have more time to molt and then migrate. And in the south, that is not the case. So we generally see that refeathering of the brood patch happens much earlier, which we interpret as higher failure rates during the brood stage. And then interestingly, with warming, we see that this is delayed and then starts to get into conflict with the wing and body mold. And there we think that this is a single-brooded species typically, but that as the laying gets earlier and earlier, more birds try to have a second breeding attempt when they fail, and then they're basically late and exhausted by the time it comes to the molt cycle. So using this phenology data gave us a bit more insight into what might be happening within the breeding cycle. And so it'd be great to kind of roll this out across other species. And so I want to finish with some examples why this model doesn't work as well as we want to when we have real-world ringing data. And so this is a case study with siskins in Scotland. Siskins are very mobile, so we don't observe them after they finished molt. And we tried, so with this data set, to fit these underhill models to them, and the fits were really bad. And so it doesn't matter if there's a model type of these models where you only look at active molt scores, and there's one where we use the old plumage data and the molt scores, and neither of those would give us very good results. And that's because one of the key assumptions of the model is that the capture probability is unaffected by the molt status. And for passerines, we know that is almost always not true. The heavier the molt is, the less able birds are to fly, so the less able you are to get them into a mist net. And you can see that so on kind of the histogram of the obtained molt scores, that kind of these central molt scores are missing. But this is a marker capture system after all. So we do have known individuals that we capture at various stages. And so we extended the existing models to use this marker capture data. And lo and behold, so because we're already essentially fitting a distributional model, we can add a random effect that has a variance that is the same as the population variance of the molt start date. And so we just tack on this kind of linear regression model, and that really works well. So even with quite low recapture rates, we can get unbiased estimates. And we know this is real data, but we know they're unbiased because we did a simulation study that essentially showed us that with as few as a handful of recaptured birds, you can avoid the bias. And very quickly, we then applied this to a system in the Southern Hemisphere where there's extremely weak seasonality. And you don't only have capture bias, but you also have molt basically throughout the year. And that means you get old, new, and active molt records all the time, which then kind of blows up some of these model variants. And again, we were able to use the recapture data and by relaxing the distinction between old and new plumage categories to get model fits. So these are our extended model fits that agree very well with direct molt speed estimates we get from birds that were recaptured multiple times. And for this study, we only had, so in a data set of about 3,500 captures, we only had about 60 individuals that were recaptured within molt. So it really works nicely. Yeah, and that's it. So I think it's great to capture biometrics when you have the bird in the hand, and that can really allow us to understand better what's happening with these populations. And we've written a lot of this up. So there's an R package for the software, and there's a paper on arXiv if you want to dive into the details. Thank you.
Thank you very much, Phil. Fascinating work. We have time for one question. Oh, one, yes.
Hey, Philip. This microphone's not working.
I can hear you, but I guess okay. Online might not.
Hi, thanks for that talk. That's really interesting work. I was wondering if you can use your inference about that molt to estimate how detectability is changing at different stages of the cycle.
Yes, for detectability as in captures in a mist net. I guess that is the easier bit. I guess then how you make inferences about that translating to detection by other means is probably a bit more dicey.
I meant detectability in a mist net.
Yeah, no, you should be able to, because you can, I mean, for every, you get an expected, you can create an expected distribution of what mode stages you would expect to see at a certain date, and then you can use the difference between the observed and expected to derive mode stage specific capture, or detection probabilities should be possible.
Thanks.
Thank you very much. Okay, so the plan was to have a break, but what we suggest is maybe to have the honorary lecture now. If Emmanuel is happy to do it, I don't know. Really? Would you be willing to do the talk now? Or?
No break. Sorry. No break.
So then you can catch up with the time. And then the plan after this amazing talk that we're going to have is to have the icebreaker, the same place we had lunch. Okay? Sorry for the... Ah, she's Sarah?
Yes, that's right. That's great.
Okay, how does it work? Okay, so apparently I have to present myself. So I'm Sarah Cubain. I'm working here at the CEF, and I'm part of the scientific committee of the Euring conference. So we're very delighted to welcome Emmanuel Kam for the honorary talk of this Euring conference. And there was supposed to be a break, so I was going to prepare a bit more, but let's just do it. Maybe I say a bit less than what I plan to say. So Emmanuel is a professor at the University of Western Brittany at Brest in France. Before that, she was an associate professor and then a professor at the University of Toulouse. And she was a postdoc at Patrick Saint and Simon Fraser University in Canada, and Ecology and Evolution Group at the Mediterranean Institute for Advanced Studies in Spain. And before that, she got her PhD in 1997 from Pierre-Marie Curie University in Paris. So Manu is a population ecologist who combines fieldwork and statistical modeling to address the demographic processes underlying population dynamics. So it would be hard to summarize her contributions to the field in a few words, but briefly, I can say that she's strongly involved in the long-term monitoring program of the Kittiwake that started in 1979 in Brittany in France, and her numerous scientific achievements over the years have focused on ecological and evolutionary responses of bird population to environmental variation. And she has worked a lot on variation in individual behavior and decisions about breeding or not, timing of breeding, mating, and site fidelity, and responses of birds to changing conditions. Apart from that, Manu's research also focused on correlations among phenotypic traits and heterogeneity among individuals and how it can affect population dynamics. She also teaches a lot, population dynamics, evolutionary ecology, etc. And she herself has a long-term individual monitoring history with the Euring community that involve major life history events like
involving a hidden pond during a previous Euring conference, or an adaptive behavior of mimicking a kitty wake at some Euring dinner conference too. On the top of that, Manu is a female professor in ecology, which is, there are not so many of them, at least in France. So she has been and still is a great role models for many junior generations of scientists, including me. So thanks a lot, Manu, for giving a talk today for us.
Thank you, Sarah. You shouldn't have said everything. Now I'm scared. I wanted to thank the organizing committee for inviting me. And usually when you are invited to give such a talk, it means that you are getting very old. And that's the way I feel when I do field work every week. And I teach during the week, so I do the field work during weekends. So I've been involved in a long-term, I mean, I've been collecting data from marked animals for over 30 years now. And I've been analyzing these data using capture mark recapture models. I've seen the huge changes that these models have, I mean, the evolution over time, over the past decades. And I've had to follow because I'm teaching. So when you are teaching, you have to know what you are talking about. So I had to follow as much as I could. And it's, and today I'm going to talk about teaching. I started wondering whether there was some missing knowledge that could prevent today's students from understanding today's papers, because they have not experienced the changes as I have, for example. And this is why I decided to conduct a small experiment on my students, which, okay, this is, yeah. Maybe this is not very ethical, but they weren't harmed. They are okay. So this is an experiment with a master's student. In France, we don't have any, wildlife biology curriculum like there is, for example, in the US or in Canada, as far as I know. So these were ecology students, certainly not quantitative ecologists. The experiment started after starting the course on capture mark recapture models, and I think that I asked them to answer my questions approximately in the middle of the semester, and we had reached multi-state models in the course. So I asked them to read old and recent papers, only application papers, case studies, with focusing on 3 classes of models: the Cormack-Joly-Sieber model, multi-state models, and multi-event models. So they had to read the papers, and then they had to explain what they had understood. There was a group discussion after that, so each student would bring a little piece of the story. They did not necessarily know what the others knew. And then we synthesized the results of all the discussion. What I tried to assess is whether there were, in recent papers at least, analytical components that were too complex, that were so complex that they were completely unable to understand even the biological or ecological conclusions. So this is what I tried to assess. And I also tried to assess if they had a clear understanding of the distinction between 4 items. These items, of course, correspond to things that were in the papers that I asked them to read. So the items are what we can see, but we don't necessarily manage to see, which can be accounted for using recapture or detection probability. What we can't see at all, which can be handled using an observable state. For example, if a bird or an animal is out of the study area. What we see, but we are not sure it's correct, which can be handled using state uncertainty. And what we will never be able to observe, but that we can estimate, like, for example, hidden heterogeneity, or there was a paper on the contribution of unmarked individuals to population dynamics. Okay, so the students had to present the papers, in an informal manner, but they had to explain what they had understood or not understood. Then there were questions from me, from the other students. And then we have had a synthesis with in several steps, because it's an iterative process. Then a final synthesis, and the overall process has taken an entire day, more than 7 hours, and it was too short. So, as you know, it costs money to teach. So this gives you an idea of the cost of this experiment. Okay, this is the very beginning of the story, because I asked them to read papers using the Cormack-Joly-Sieber model, but I didn't ask them to read those papers because they are too technical. It's officially, from what I know, it's the birth of the Cormack-Joly-Sieber model in 1964, 1965, even though when you read those papers, the authors refer to older papers published in the 1950s, I think. So I'm not sure, I'm not an expert, but anyway, I wasn't born, and they are too technical, and my students were obviously not born either, so I skipped this step. Okay, this is the first paper that I asked them to read. It's a very famous paper, and it's too bad that Jean-Dominique has left, because well, he's busy elsewhere, but it's a very important paper, because I think that generations of researchers have read the paper and have found it very, very enlightening. It was published in 1992, and as the authors pointed out in this paper, there's been a shift in the 1980s from estimation to population size to estimation of survival in the first step. Okay, so this is the first. Oh, I forgot to say that there are case studies in the previous paper. You know, the European deeper example, I think, the SWIFT example that we all have been using to teach are presented in the previous paper. And indeed, in the 1980s, people started publishing the very first estimates for different species obtained using capture-mark-recapture models. So I provided my students with a series of papers on albatrosses. And so at that time, in the 1980s, there were a couple of pieces of software that were available to estimate survival, including SURGE, of course. And so biologists could use SURGE with a little help from experts like Jean Claubert, for example. Okay, this is the first paper. more than 20 years ago, more than 20 years later, the same group published another paper still focusing on the estimation of survival. So the story was not over in year 2012. Well, of course, they also estimated other parameters of interest like breeding rate or breeding probability. But still, I mean, there was much emphasis on estimation of survival. And so this is a paper on the wandering albatross. So Christophe is here, I think. Please correct me if I'm if I'm wrong. This is this is a paper focusing on a species that has a specificity because it's a species where not many individuals manage to breed 2 years in a row. So individuals take a sabbatical year every 2 years, or perhaps more frequently than that. But when they don't breed, they don't come to the breeding grounds, and they are not observed. In fact, they are unobservable, and this has been handled using a model accounting for temporary immigration. So first, and second, when investigators go and collect data from birds, they don't necessarily know in which state the individual is. So I don't know the specificities of the field work on the wandering albatross, but apparently it's easier to identify a breeder than a successful breeder or a failed breeder. And this has been accounted for using state uncertainty in this model. Okay, this is in the paper. I'm sorry, but this is how they describe the model. It's a multi-event formulation of the model that has been built in eSearch. And in fact, in this paper, these are states that that can't necessarily be observed, failed breeders and successful breeders. But what people see in the field is basically breeders, failed breeders, or successful breeders. So there is this parameter stands for the probability of correctly classifying the bird as a failed breeder or a successful breeder. Once they start breeding, if they survive, the individuals take a sabbatical year, and they are not observable. They are called previously failed breeders and previously successful breeders. And there is also a state for dead birds that are not recited either. Okay, so this was for 2012. New paper in 2018, again on the wandering albatross. And you know, albatrosses are very long-lived, so in this group, they managed to look at the effect of age on survival after waiting for a very, very long time. And so concerning the survival part of the model, they have looked at the effect of sex and of groups. And unfortunately for my students, the groups are not observable because they are hidden. When you look at a bird in the field, you don't know the group that bird belongs to. So there are hidden groups. This has been handled in the model using a finite mixture. Okay. So what about the feedback of the students? Concerning the albatross system, the fact that individuals are not recited before recruitment, for example, because they remain at sea, has been easily understood. And so the idea of accounting for this using detection probability is easy to understand, apparently. The fact that individuals are not detectable, or I mean, they are not possible to observe, in fact, is also easy to understand for beginners. But there are many things that are not easy to understand in those papers. Uncertainty concerning the breeding state, whether it's a successful breeder or not, for example. This is difficult for them to understand because they lack experience with fieldwork. They have no idea how things work. So it's probably a problem of including more fieldwork in the curriculum of our students, but that's the most difficult part. I think it's extremely costly to conduct field projects, and of course it's impossible to take the students and put them on the wandering albatross colony somewhere on Crozet Island. Okay, the other thing that was very difficult for them to understand is the hidden part of the model, the hidden heterogeneity. What is almost or virtually impossible to understand for them is how can we assign individuals to groups based on things, traits, whatever, that are unobservable. This is simply extremely difficult to understand. So what I did is that I also asked some students in the group to read this paper that was published in 1986. So it's an old paper. And this one focuses on the role of heterogeneity in animal population dynamics. In this paper, Johnson, Burnham, and Nichols explain what heterogeneity is. And then they explain that they are going to focus on a specific situation that is what they call the more difficult situation, that involves heterogeneity that is not recognized or perhaps not even recognizable. Okay, in this paper, what is really neat for the students is that they use words and phrases to explain complex concepts. They take two examples of the effect of heterogeneity on age-specific mortality and the effect of heterogeneity on nest survival. Also, they discuss the implication of heterogeneity on the dynamics of hunted populations. But I think there is a talk about this during this session, this week. So for several reasons, it happens that I had written to the authors to ask them why they wrote this paper in 1986, because I was really intrigued, and this is their answer. First, they said that it wasn't clear. They did not remember exactly why they did this, but concerning Doug Johnson, he said that he was aware of other work that was conducted in human demography, because human demography, there has been a very long controversy concerning the existence of heterogeneity. And in this paper, in Doug's paper, They took an example from older papers published on human demography. And this was very well understood by the students. They were extremely enthusiastic concerning this paper because they had the impression that they had understood something. Concerning Jim, I'm sorry for the text. I didn't want to change the text or to cut the text, but this is the message that he sent me. But basically, what he said is that he was mostly interested in the effect of heterogeneity in hunted populations. This has been summarized in a later paper published in 2014, and I know that there is still ongoing discussion concerning this topic. The idea is that hunters may remove a particular class of individuals from populations, perhaps frail individuals or perhaps individuals in bad condition, and if this holds, the expected result or the expected consequences on population dynamics may not be the same as if hunters were taking, individuals that are in the whole range of body condition, for example. Okay, so this also was, the feedback of the students was very positive. They had the impression that they had understood something important. Okay, let's finish with the albatross study. This is the last paper that I asked to the students to study. And it's a paper, a very recent paper, that addresses the influence of dispersal on lifetime reproductive success. So this paper includes several species, but here's the wandering albatross. This is the model that they have used. Again, it's in the paper, so the students had to study this. And well, it's not that different from the previous figure that we looked at, but there are still differences. For example, there is no state uncertainty in this paper. I'm not sure why. It's probably because it's not the same period of time that has been used in the paper. And also there are more states, like there is a distinction between breeding failure at the egg stage, breeding failure at the chick stage, and so on. But otherwise, the general structure of the model is like the other one. What happened? Okay, concerning this paper, as before, the group that studied the paper had no problem with the fact that birds do not come to colonies before recruiting. Individuals take sabbatical years, and we cannot see them. And I was surprised because in this paper, there's a method that is used to calculate the total number of offspring produced by adults, and which is not a simple method. And they told me that everything was fine. My guess is that it's partly because there was no state uncertainty in the model. Once they had understood that, a bird can be alive, but you don't see the bird, estimation of longevity must not be that much of a problem in their mind. Anyway, but okay, as a conclusion of this experiment with albatross papers, apparently the take-home message is that there are old ideas that we use to justify the approaches that we use in today's papers, and that are better explained in old papers. And this is normal because we don't have time to do this. We don't have room in our own papers. the ideas are not new, so we don't spend much space. I mean, we don't use much space. We don't spend much time explaining this, but this can be a real problem for students. So there is a learning, obviously there is a learning process that includes, prior work that is necessary to understand today's papers. Okay, another experiment with Kittiwake papers. The Kittiwake program is a program that I know because this is the one that I've been involved in for more than 30 years. And so the first paper that I asked my students to read is this one from my PhD on intermittent breathing. And I also asked them to read this fabulous paper that appeared just before my PhD from Nichols and Kendall. So they had a very nice idea. They published exactly the perfect paper that I needed to start my PhD on the use of multi-state models to address questions in evolutionary ecology. And this one is not that technical. I mean, it includes examples of questions that we can address using multi-state models. Concerning the Kittiwake program, obviously we are not facing the same difficulties as with albatrosses. It's a completely different setting. It's not as long-lived as a wandering albatross, for example. It's closer. This is the population that we are studying in Brittany. So the fact that it's closer makes it possible to have, perhaps more frequent visits to colonies. I don't know. In this study system, there have been up to 6 colonies occupied in Brittany. I mean, on the coast of the mainland. And this is what colony number 5 looks like. You have different cliff walls where kittiwakes breed. And it's relatively easy to observe them in this location because, you can get close to the birds. All you have to do is sit here and look at the birds breeding there on the other side. Sometimes it's not that easy because of weather condition, and we also obviously have kittiwakes breeding in weird locations like some sort of marine caves. So it happens sometimes that we have to swim to look at some nests, but well, anyway, it's in this study system, the main problem is not detection probability. Over time, when this program started, the initial goal was to work on population dynamics and colony dynamics. These are the 6 colonies, continental colonies, and as you can see, some colonies have gone extinct over the study. And new ones, like this one, number 6, has been colonized during the study. So this was the first goal. And my colleagues wanted to understand the processes underlying those dynamics. But other people involved in the project had a completely different research topic. Etienne Danchin here was interested in behavior and social behavior. And this is a paper that I didn't ask to my students to read because it's a so different research area, but you can see at the beginning of his career, Etienne was publishing very detailed behavioral studies. He was even describing the behavior of the species with many words and many phrases. It's this species, you know, it's a very noisy species. There are lots of social interactions, and with a little bit of experience, when you watch a behavioral sequence, you are able to tell, you know, for example, something about the territorial status of a bird that is, you know, standing somewhere. Like obviously there's an intruder here. And all the neighbors are protesting. So again, this is, you know, the work by Etienne Danchin. He has also been working on sexual interactions. Like in this slide, it's obvious from Etienne's work that this is a male and these are two females. Okay, so the consequence of this initial focus is that we have a very high field effort. We have dozens and dozens of behavioral codes to use each time we watch a bird or a pair or a group of birds. And this explains the type of mark recapture histories that we work with. For example, here, these are birds that were marked as chicks, and many of them don't come back. They either go elsewhere or they die. But if they come back, after they come back, the detection probability is very high in this system. So recapture probability or detection probability was not the main problem that we had for, several sub-projects. But there are still zeros in those histories, especially during the pre-breeding stage, before they become breeders. And this is why when I started my PhD, I decided, my supervisors suggested that I should go and visit Nichols and his group, and that I learn how to build multi-state models. And at that time, yes, I don't think that program Mark was available, but I used a program MS Survive, developed by Jim Hines and his group. So what happened? We found something that is extremely, not surprising at all. We had breeders and non-breeders, birds that are taking a sabbatical year. And in this figure, in this old paper, we can see that breeders have a higher survival probability than non-breeders, and breeders have a higher probability of breeding again than birds that were taking a sabbatical year. So this is easy to understand, at least for evolutionary ecologists, because this immediately suggests a heterogeneous population when we don't detect trade-offs between life history traits. I also asked one of my students to read this old paper, which is a biology paper, but it's a paper published, in this book by Thomas and Coulson, and this is what they write about kittiwakes, same species. There is a high degree of similarity between the reproductive performance of the same individuals in consecutive and subsequent years. A tendency also reported in other avian studies. At that time, people started talking about quality, individual quality, which is still debated today, but it's another name given to heterogeneity, in fact. Okay, heterogeneity. In Patuxent, there was somebody, Belink, who had discovered a new toy, a new program that he wanted to use. He's a statistician, and he decided that he wanted to learn how to use bugs. At that time, it was not WinBugs, it was bugs. And for some reason that I don't remember, we collaborated, and he has written a paper, on the kittiwake system, and he has also tried to explain to wildlife biologists why they should also use bugs. And I published another paper at the same time, intended for biologists. So I asked to my students to read both articles. From this collaboration, emerged something that is very difficult to understand for the students, apparently. So this is the distribution of individual survival probability and breeding probability. But it's a whole distribution. And obviously, when you see a bird somewhere in the field, you have no clue where the individual is in this distribution. So it's completely unobservable, but we can estimate it. And the last paper I asked to my students to read is, it's a couple of papers. A recent paper written by, published by Paul, who is somewhere in this room, I think, and an old one. This one is the biology paper. It's basically the result of several years of research on social interactions, habitat selections, and habitat selections, sorry. So published in year 1998. And this recent one is some sort of synthesis between the work of my colleagues working on behavioral ecology and the other people working on life history, evolution. It's an attempt to bridge the gap between social factors, habitat selection, and population dynamics. For this paper, Paul has been using JAGs. This one is absolutely not using capture mark recapture models, at least not including recapture probability. From Paul's paper, I chose this figure to illustrate what the students could not understand. It's a paper based on an integrated population model, and there is something here, this series of estimates here that correspond to immigrants that are unmarked. So this is the main difficulty that my students encountered. How do we know that a bird that is not marked is an immigrant? Because we also have unmarked birds that are locally born. Not everybody in the population was marked. So, so concerning the kittiwake papers, the initial multi-state model was easy to understand, apparently, for the students. Concerning hidden heterogeneity, things had gone better, after reading and discussing mixture models and after reading Johnson's paper on heterogeneity. But then the situation deteriorated again with random effects. How can we know the individual survival probability because the bird dies only once. Like there's no probability for that individual. So this is something that we just don't get. And concerning the integrated population model, this is obviously something they haven't been able to explain to me why they did not understand the point of all this complex modeling process. So I don't know exactly why, but obviously they were not able to read, to understand the paper. 2 papers were based on Bayesian analysis, and this is probably part of the problem. Okay, so concerning this teaching experiment, it seems that many recent papers concerning applications, case studies, are difficult to understand for students at the master's level. Again, these are not, quantitative wildlife biology students, and they are not statisticians. Long-term studies are addressing increasingly complex questions. Well, if they have to write something, it has to be something new. They are building on previous work, and they don't necessarily give many details about the reasons why they are doing this that way. This raises conceptual difficulties. So there are technical difficulties. And when the students are struggling, to understand what individual heterogeneity means, they miss the point and the conclusion after that. What's obvious is that reading old papers helps a lot, because this helps them reconstitute the ontogeny of the ideas. Either technical, but gentle papers, technical, not too complicated, like the monograph by Le Breton or the paper on multi-state models. And also reading old biology and ecology papers helps a lot sometimes. To conclude, there is a paper that I was happy to read when I discovered it, that has been published in year 2002 by Kendall and Gould. And the title of this paper is An Appeal to Undergraduate Wildlife Programs, Send Scientists to Learn Statistics. Well, I was not an author of this paper, but I think that we could, change the date here. We could publish almost the same paper today, and I think that things have deteriorated. To access to the conclusions, even the biological and ecological conclusions of the papers that we write today, we need more teaching time to help the students understand our conclusions. We need to teach more. We need time and money to teach. And here, the small experiment included only 2 species and 4 papers focusing on those 2 species. There were only 2 categories of models, 3 in fact, but those 2 ones are closely related. Now, just listening to some talks today, it appears that there are many more challenges that our students must take. So I'm a little bit worried because at least in France, our curricula are absolutely not incorporating this change in complexity of the tools that we need to analyze data from marked animals or unmarked animals. I would like to emphasize that there are a lot of resources, thanks to the work of dozens of people all over the world, tools that are available to us and to our students. Of course, this very famous Mark book, for example, The Mark book is a book about program Mark, but there is way more than that in the Mark book. Only when the students realize that there are 22 chapters and that we are just beginning, the course, they are scared to death. So we need to help them, we need to explain a method so that they can use the book without being completely overwhelmed. On this website, there are also course notes that can be very useful. Colleagues who have made their notes available. This is really, really useful too. Workshops, including online workshops, are fantastic. Some of them are completely online, others are not completely online, but anyway, you must find a way of advertising them. Well, the first workshop that I attended was, I don't remember when it was, in fact, somewhere between 1993 and 1995. It was a surge workshop, then dozens of other workshops, and the last one was this one. I missed many workshops. I wish I could have participated, but no. And that's it. If you have any questions.
So we have time for a few questions.
Thank you very much for a very interesting talk and a very interesting experiment. So I have also occasionally read some old papers, and I've not always had the same experience as your students, because there's also some old papers that are absolutely hideous. So I was wondering, given what we see, do we perhaps need more or better textbooks as well? Like places that actually summarize the concepts in a more concise way, since we cannot ask the students to just read ever more and more old literature in addition to the new ones as well. What are your thoughts, and what would we need concretely to make a change, not in 15 years, but starting soon?
I'm not sure I'm not sure I know. There are textbooks regularly appearing and published. But from what I don't know every textbook that has been recently published, but many of them are pretty specialized. And I don't know how to avoid specialization. This is the problem that I have at the moment. We need to devote more time to specialized things and to teach specialized things. And this is something that is not easy to explain to the board in your university. I don't know about your place, but at least not in mine. Well, again, if you have any thought about this, I would be happy to discuss this with you. We started this morning at breakfast with two persons who are also teaching. And what's impressive is that one of the persons, I don't know where he is, told me that he would start at the undergraduate level with JAGs, directly with JAGs. Is this the way to go? Perhaps.
So thanks for a really nice talk. You mentioned the lack of fieldwork experience as being a problem for understanding some of the issues that you face and why these things are difficult. I was wondering if films might be able to help with that, kind of filming fieldwork and letting students see what it actually looks like. Because I think, you know, if their background, if their idea of what it looks like is a David Attenborough film, then it might help them to just see sort of, yeah, why it's difficult to see some of these different things in that way. It's maybe what's in their head, what they're imagining is very different from what it actually looks like.
No, I mean, it could be a good idea. I'm not taking the risks with my students, you know, because I work in vertical cliffs. So I'm afraid of asking them to come. A few of them accept to come on weekends, but so I don't know how to show them what really happens when you spend a day outside and look at marked birds. But videos could be very helpful, I find, yes. Have you tried this?
No, I have not.
We have a virtual question. When using unobservable states, how general can the model be? Must the model be highly constrained to achieve convergence?
When using unobservable states? No.
Yes. How general can the model be when it includes unobservable states? And must the model be highly constrained to achieve convergence?
Oh, well, that's a question for Christophe. Christophe, do you use it? Well, okay. You are the one who have used, I mean, in this series of papers, you've used an observable state. And I don't know if you've had convergence issues. This is one of the questions. I don't know.
No, I used a fantastic software that was done by Rémi Choquet and and developed by Roger Pradal. I don't know if it's here, but no, but it was there was no major problem for convergence.
Well, okay, I think it means we have to go to the icebreaker. So thanks a lot, Manu, and you can still talk to her at the icebreaker. Thank you so much.
So it's time for the icebreaker. The idea is to get together, get to know each other, catch up with our friends. So it's going to be the same place as for lunch. You go out on the left, you follow the signs and the people with green badges. Take your bag, stuff with you. We won't come back here. Okay? Well, until tomorrow morning.
La même expérience avec mes étudiants.